You are not standing still. Right now, as the room around you goes quiet and the weight of the day begins to lift, the ground beneath you is moving. The planet you are lying on is spinning at roughly 1,000 miles per hour. It is also hurtling around the sun at 67,000 miles per hour. The sun itself is sweeping through the outer arm of the Milky Way at 450,000 miles per hour. And the Milky Way, along with every galaxy in our local neighborhood, is flowing through space in a direction that took humanity most of the 20th century to even begin to identify. Everything is moving. Everything has always been moving. The stillness you feel right now is one of the most convincing illusions in the universe. For most of human history, that illusion went completely unchallenged. The ground felt solid. The stars came back every night in the same positions. The sky was the one thing that did not change in a world that changed constantly. And so people built their calendars around it, named their gods after it, and trusted it with the kind of faith that only comes from something that has never once let you down. The sky was letting them down the whole time. They just did not have the instruments to know it. What we have learned in the last 100 years, and especially in the last few decades, is that the motion embedded in our address goes much deeper than the orbit of the Earth or the rotation of a galaxy. There is a larger current, a flow that sweeps across hundreds of millions of light years, carrying the Milky Way and 100,000 other galaxies in a coherent, organized direction through the universe, a basin in the gravitational landscape of the cosmos so large that humanity only managed to map its boundaries for the first time in the year 2014. The people who named it reached into the Hawaiian language and pulled out two words, Lani, meaning sky or heaven, Akea, meaning spacious, immeasurable. They chose those words deliberately, and the choice was not merely poetic. The Hawaiian navigational tradition, one of the most sophisticated wayfinding systems ever developed by any culture on Earth, is built on a single foundational insight that Western astronomy spent centuries rediscovering. You do not find your place in the world by standing still and looking at a fixed map. You find it by reading how things move around you, the swells of the ocean, the arc of the stars, the flight of birds far from any visible shore. Motion is not noise to be filtered out. Motion is the message. That is what this story is about. It is about how a species that once believed the sky was a painted ceiling, slowly, painfully, across generations of wrong assumptions and corrected maps, learned to read the motion of the universe itself, and in doing so, discovered that the address we thought we knew, Earth, Solar System, Milky Way, was only the first few lines of something much longer, something that ends, at least for now, with a name that means immeasurable heaven, in a language spoken by people who have always understood that the sky moves, and that moving skies, read carefully, tell you exactly where you are. The current is real, the basin is real, the address is real, and tonight we are going to follow it all the way out to the edge of the largest thing we have ever called home. On a clear night in the desert, far enough from any city that the atmosphere above you is genuinely dark, the Milky Way looks like something spilled across the sky, a broad, uneven river of light, brighter in some places and dimmer in others, stretching from one horizon to the other with a density that makes it look almost solid. People who grew up under light-polluted skies and see it for the first time often stop mid-sentence. They stand there with their heads tilted back and their mouths open, and for a moment they stop talking about whatever they were talking about and just look. What they are seeing is about 200 billion stars. Most of them are so far away that no human eye could distinguish them individually. Their light blurs together into that broad, luminous band, and the dark patches cutting through it are not gaps in the stars, but clouds of interstellar dust blocking the starlight behind them. The whole thing is rotating. All of it, at speeds that would be incomprehensible if you tried to experience them directly. But because the distances involved are so vast, none of that motion is visible. The galaxy looks like a painting, It looks like something permanent. Ancient astronomers, working without telescopes, without any framework for understanding what stars actually were, made extraordinarily careful observations of that sky. The Babylonians tracked planetary motions across decades and developed mathematical models precise enough to predict eclipses centuries in advance. Egyptian architects aligned their pyramids to specific stars, with an accuracy that modern surveyors find impressive. The ancient Greeks catalogued hundreds of stars, measured their positions, grouped them into constellations, and handed that catalogue to the Romans, who handed it to the medieval world, who handed it, more or less intact, to us. Walk outside tonight and the constellations you see are the same ones Ptolemy described in the 2nd century of the Common Era. The stars have barely moved in the time since. That apparent permanence was not a failure of observation. It was an accurate account of what the available instruments could detect. The stars do move, over thousands of years. The shapes of the constellations do change. Astronomers call this proper motion, the slow drift of individual stars across the sky as they follow their own paths through the galaxy. But the changes are so gradual, so far below the threshold of anything detectable without modern instruments, that for all practical purposes the sky looked fixed. The same patterns rose and set every night, year after year, century after century. If you were going to build a worldview around reliable things, the stars were an obvious foundation. So people did. Entire systems of meaning grew up around the assumption that the sky was the one domain of existence that did not change. Aristotle argued that the heavens were made of a fundamentally different substance than the earth, something he called ether, a perfect and unchanging material that explained why the celestial objects moved in smooth circles without ever altering their fundamental nature. The sublunary world, everything below the orbit of the moon, was subject to change, decay, birth, and death. The superlunary world was not. It was eternal and perfect, and the evidence for this was simply that it appeared to be, for a very long time. That argument was persuasive because no counter-evidence existed. The telescope had not been invented. The concept of a galaxy separate from the Milky Way had not been formulated. The idea that the Sun was itself a star, one of roughly 200 billion in our galaxy alone, would have seemed not just wrong, but absurd to most educated people in most of the world, until surprisingly recently in the history of human thought. The sky earned its reputation for permanence. It worked for navigation, for agriculture, for religion, for philosophy, for the structuring of human time and human meaning across thousands of years of civilization. The fact that the reputation was built on incomplete information does not diminish the achievement of the people who built it. It just means that when better information arrived, the story had to get bigger. There is one culture, though, that built something different into its relationship with the sky from the very beginning. Not an assumption of permanence, but an assumption of motion. A navigational tradition founded on the understanding that the sky and the ocean were dynamic systems, and that your position within them was determined not by finding fixed landmarks but by reading flows. The Polynesian navigators who settled the Pacific Islands, over the course of roughly 3,000 years, accomplished something that remains remarkable by any standard. They crossed thousands of miles of open ocean in double-hulled canoes, with no magnetic compasses, no GPS, no charts in the European cartographic tradition, and no fixed landmarks visible for most of the voyage. They navigated by stars, but not simply by identifying star positions. They used what is called a star compass, a mental framework that tracks the rising and setting points of more than 100 stars across the full circle of the horizon, allowing a navigator to hold their heading through the night by moving continuously from one star reference to the next as the sky rotates overhead. But they also read the ocean itself. The Pacific has deep ocean swells generated by distant wind systems, and these swells travel thousands of miles from their sources with a consistency and directionality that a trained navigator can detect through the hull of a canoe. Different swells come from different directions, and an experienced wayfinder can identify multiple swells simultaneously and use them to maintain bearing even on overcast nights when no stars are visible. They read the colour and temperature of the water, which changes with depth and with proximity to islands. They track the flight patterns of birds, which range predictable distances from land and return to roost at predictable times. They read the shape of clouds, which form differently over islands than over open water. Every piece of that system is a reading of motion. The arc of a star is motion. The swell of the ocean is motion. The flight of a bird is motion. Polynesian navigation is not a system for locating yourself relative to fixed points. It is a system for understanding your position within a field of flows and currents and patterns, and using those flows to guide you where you want to go. This matters for our story because the method that eventually revealed Laniakea, the method that allowed astronomers to map the largest structure we have ever identified as our home, is built on exactly the same foundational insight. The structure is not visible in the positions of galaxies. It is visible in their motions. You cannot see Laniakea by looking at where galaxies are. You can only see it by watching where galaxies are going. The Polynesian navigators understood something about the universe that Western science would not formally articulate at the cosmological scale until the 21st century. That understanding is why their language was chosen to name what we found. The sky was never still. The ocean was never still. The universe was never still. And the people who learned to read that motion, whether they were crossing the Pacific in a canoe or reconstructing a gravitational landscape from a catalogue of galaxy velocities, were doing the same essential thing. They were finding their place by watching how everything around them moved. On the night of October 4th, 1923, Edwin Hubble climbed to the observing platform of the 100-inch Hooker telescope at Mount Wilson Observatory, in the mountains above Pasadena, California, and did something that would eventually force human beings to rewrite the size of everything they thought they lived in. He was not trying to change the world that night. He was looking for novae, exploding stars, in a smudge of light that astronomers had been cataloguing and largely ignoring for years. The smudge was called the Andromeda Nebula, and the working assumption among most astronomers at the time was that it was a cloud of gas somewhere inside the Milky Way, one of many such clouds scattered through the galaxy, interesting in the way that most astronomical objects are interesting, which is to say mildly and without any particular urgency. Hubble found something on his photographic plate that night that did not behave like a nova. It pulsed. It brightened and dimmed in a pattern that he recognized almost immediately, a slow, regular rhythm that identified it as a Cepheid variable star. Cepheids were valuable to astronomers for a reason that had been worked out more than a decade earlier by an astronomer named Henrietta Swan Leavitt. Working at the Harvard College Observatory under conditions that reflected the limited options available to women in science at the time, Leavitt had been assigned to measure the brightness of stars in photographic plates, work considered too tedious for the male astronomers on staff. And in the course of that work, she identified a relationship that would eventually change the scale of the known universe. The slower a Cepheid variable pulsed, the more intrinsically luminous it was. This period luminosity relationship meant that a Cepheid was effectively a standard candle, an object whose true brightness you could calculate from its behaviour, and whose distance you could then determine by comparing that true brightness to its apparent brightness in the sky. Hubble knew the relationship. He measured the period of his Cepheid. He did the calculation. The number he got was not possible for a star inside the Milky Way. The Cepheid in Andromeda was nearly 1,000,000 light-years away, a distance that placed it far beyond any structure that could belong to our galaxy. The smudge of light that astronomers had been cataloguing as a gas cloud was not a gas cloud at all. It was an entire galaxy, a system of hundreds of billions of stars, as vast and complex as the Milky Way itself, existing completely independently of it at a distance so enormous that its individual stars blurred together into a faint smear, visible to the naked eye only on the clearest nights. Hubble crossed out the letter N he had written on his photographic plate, the N for nova, and wrote 3 letters above it, variably star. It was the kind of annotation that looks modest on paper and carries the weight of a revolution. The implications took time to sink in, even for Hubble himself. If Andromeda was a separate galaxy, then the other spiral nebulae scattered across the sky almost certainly were too. The universe was not the Milky Way plus some wisps of gas and a few nearby star clusters. The universe was filled with galaxies, each one an island of billions of stars, separated from one another by distances so large that crossing them at the speed of light would take millions of years. The cosmos had just grown by a factor so large that no familiar unit of measurement could make it feel real. Hubble spent the years following that first Cepheid measurement extending and refining the work. He measured distances to more galaxies. He built up a catalogue, and in doing so, he accumulated data that pointed towards something even more disorienting than the mere existence of other galaxies. The galaxies were moving away from us. Almost all of them. When Hubble analysed the light from distant galaxies, he found that their spectra were shifted toward the red end of the electromagnetic spectrum, a phenomenon called redshift that occurs when a light source is moving away from the observer. The further away a galaxy was, the more its light was redshifted, and the more redshifted its light was, the faster it was receding. This relationship between distance and recession velocity, now called the Hubble law, had an unavoidable implication. The universe was not static, it was expanding. A space between galaxies was stretching, carrying the galaxies apart from one another, not because they were moving through space like rockets firing their engines, but because the fabric of space itself was growing. The Belgian priest and physicist Georges Lemaitre had suggested something along these lines theoretically before Hubble's observational confirmation. And Einstein had resisted the idea because it violated his intuition that the universe ought to be eternal and unchanging, an intuition he later described as the greatest blunder of his career. The data did not share Einstein's intuition. The universe was expanding, had been expanding since the beginning of whatever the beginning was, and showed no signs of stopping. For the purposes of our story, the expansion of the universe is not just a remarkable cosmological discovery, it is the backdrop against which everything else in this story happens, the context that makes the mystery we are trying to solve a mystery in the first place. Because if every galaxy in the universe were simply riding the expansion of space and nothing else, there would be no story to tell. Every galaxy would recede from every other galaxy in a smooth, predictable, perfectly uniform way. Maps would be straightforward. Distances would be unambiguous. The universe would be expanding, and that would be all there was to say about its large-scale behaviour. But the universe is not smooth. It has never been smooth, from the very earliest moments after the Big Bang. Tiny quantum fluctuations in the density of the primordial plasma meant that some regions were slightly denser than others. Those slightly denser regions had slightly stronger gravity. That slightly stronger gravity pulled in more material, which made the density higher, which strengthened the gravity further. Over hundreds of millions of years, the small became large, the slight became significant, and the universe developed the rich, complex structure of galaxies and clusters and filaments and voids that we observe today. Structure means lumpy. Lumpy means uneven gravity. Uneven gravity means that galaxies do not just ride the expansion, they also feel gravitational pulls toward the concentrations of mass around them. And those pulls give them motions above and beyond what the expansion alone would predict. Hubble saw the expansion, what he could not fully see. With the instruments and catalogues available to him in the 1920s and 30s, was the layer of motion underneath the expansion, the subtle, structured, organised flows that the gravitational landscape of the universe imposes on top of the smooth Hubble recession, the currents beneath the tide. Those currents would take another half-century to begin to map, and mapping them would require not just better telescopes, but a fundamentally different way of asking the question, not where are the galaxies, but where are the galaxies going? And why? The night Hubble measured the distance to Andromeda, the universe became larger. What no one fully understood yet was that it had also, in a different sense, become more organized. The expansion was real, but underneath it, something else was happening, something that would eventually require a Hawaiian word to name. Sometime in the middle of the 1970s, astronomers began noticing something in their data that did not have a clean explanation. The galaxies in the local universe were not receding from one another at exactly the rates predicted by the Hubble law. Most of them were close enough to the predictions that the deviations looked like measurement noise, but a few were not. And as the catalogues grew and the measurements improved, the deviations stopped looking like noise and started looking like a pattern. Galaxies in certain regions of the sky were systematically moving faster toward us, or slower away from us, than the Hubble flow alone would predict. Something was displacing them. Something was adding a component of motion on top of the smooth expansion, pushing some galaxies faster and pulling others off their expected trajectories. Astronomers gave this extra motion a name: peculiar velocity. The word peculiar here does not carry its everyday meaning of strange or odd, though the phenomenon would eventually justify that meaning too. It is an older usage, meaning specific or belonging to a particular thing. A galaxy's peculiar velocity is the motion that belongs specifically to that galaxy, the motion it has over and above its share of the cosmic expansion. Peculiar velocities exist because gravity is not uniformly distributed across the universe. Wherever matter concentrates into clusters or filaments, the gravitational pull is stronger, and nearby galaxies accelerate toward those concentrations, acquiring additional velocity that the Hubble flow did not give them. A galaxy falling toward a massive cluster is like a ball rolling down a slope. The ball's total motion is the sum of whatever velocity you gave it initially, plus the velocity it picked up from rolling. Strip away the initial velocity and what remains is a record of the slope. The slopes in the universe are the gravitational landscape, the uneven terrain carved by the distribution of mass across hundreds of millions of light years. And reading those slopes requires measuring peculiar velocities, which requires, first, being able to accurately determine both the velocity of a galaxy and its distance, and then subtracting one from the other carefully enough that the residual peculiar velocity signal is not swamped by measurement errors. This is genuinely difficult. Galaxy distances are hard to measure. The most reliable methods involve standard candles or standard rulers, objects or relationships whose intrinsic properties are well enough understood that apparent brightness or size can be converted to a distance. Cepheid variables work well for nearby galaxies, but become too faint to measure at large distances. Tupeia supernovae, exploding white dwarf stars that all detonate at roughly the same intrinsic brightness, can be seen across billions of light years, but occur only occasionally in any given galaxy. Other methods, like the Tully-Fisher relation, which connects the rotational speed of a spiral galaxy to its intrinsic luminosity, are more broadly applicable but carry larger individual uncertainties. The accumulated uncertainty in distance measurements means that any individual galaxy's peculiar velocity is known only approximately, but the law of large numbers is forgiving. Measure enough galaxies across enough of the sky, and the random errors begin to average out, leaving behind a signal that reflects the true underlying flow field. The more galaxies you measure, the cleaner the signal gets. By the late 1970s and through the 1980s, several groups of astronomers were building exactly these kinds of large, peculiar velocity catalogues. What they found, as the catalogues grew, was that the peculiar velocities in the local universe were not random. They formed coherent patterns. Large numbers of galaxies spread across wide regions of sky were all moving in the same general direction, as if being swept along by a current that extended across hundreds of millions of light years. The Milky Way itself had a peculiar velocity, a significant one. This was established by a different kind of observation entirely: the cosmic microwave background, the faint glow of thermal radiation left over from the early universe, fills the entire sky with extraordinary uniformity. It was emitted roughly 380,000 years after the Big Bang, when the universe had cooled enough for electrons and protons to combine into neutral hydrogen, and it has been travelling through the expanding universe ever since. Its temperature is the same in every direction, to 1 part in roughly 100,000. Except for one systematic difference. One hemisphere of the sky is very slightly warmer than the other. Not by much. The difference is about 1 part in 1,000. But it is real, and it has a clear physical explanation. The Milky Way is moving through the universe, moving relative to the frame in which the cosmic microwave background is at rest, which is effectively the frame of the universe as a whole. The hemisphere toward which we are moving appears slightly warmer, because the radiation from that direction is blue-shifted, compressed to slightly shorter wavelengths and therefore slightly higher energy. The hemisphere we are moving away from appears slightly cooler for the opposite reason. By measuring this temperature asymmetry precisely, astronomers can calculate not just that the Milky Way has a peculiar velocity, but exactly how fast it is moving and in what direction. The answer they get is roughly 600 kilometers per second, directed toward a point in the southern sky in the general direction of the constellation Centaurus and beyond. 600 kilometers per second is not a small number. It is vastly larger than anything that could be explained by the gravity of the few nearby clusters and groups whose masses were well measured at the time. Something larger, something more massive, something located in the general direction of Centaurus and probably considerably beyond the structures already identified there, had to be exerting enough gravitational pull to accelerate the Milky Way and everything around it to that speed. The question that nobody could yet answer was what it was. The galaxies in the local universe were flowing. The Milky Way was flowing. Everything within hundreds of millions of light years appeared to be flowing in roughly the same direction, pulled by something that the maps of the time did not contain, something whose location pointed toward a region of the sky that was, by a combination of bad luck and orbital geometry, one of the hardest places in the entire sky to observe. Behind the plane of our own galaxy. The current was real. The slope was real. The mass concentration responsible for it was real. What it was, and how large it was, and whether it was a single structure or a complex of structures, remained almost entirely unknown. Answering those questions would require new instruments, new methods, and a willingness to spend years doing the kind of painstaking survey work that rarely produces dramatic daily headlines, but that occasionally, when enough measurements have accumulated, produces a map that changes how an entire civilization understands where it lives. That work was beginning, and the people doing it were starting to suspect that the answer, when it came, would be bigger than anyone had expected. Every address starts somewhere familiar. Yours probably begins with a street number, a city, a state, something specific enough that a stranger could find you, something that places you in a context other people recognize. The address we are building in this story starts the same way, with something familiar, something you already know, before it moves outward into territory that most people have never had occasion to think about. So start here. A planet, roughly 8,000 miles in diameter, orbiting a star at a distance of 93 million miles. The planet takes 365 days to complete one orbit. It spins on its axis once every 24 hours. It has one moon, one ocean divided by continents into several named bodies of water, and somewhere between 8 and 10 million species of living things. Depending on how you count and how many remain undiscovered, you know this place. You have been on it your entire life. What is less obvious, because nothing about the sensory experience of standing on the Earth's surface communicates it, is that the Earth is moving in several different ways simultaneously, and has been moving this way since long before any living thing existed to notice. The spin of the Earth on its axis, which is what produces the experience of day and night, carries a person standing at the equator through space at roughly 1,000 miles per hour. The orbit of the Earth around the Sun adds another 67,000 miles per hour. The spin of the Earth's axis is tilted relative to its orbital plane, which is why the angle of sunlight changes across the year, and why seasons exist. None of this motion is perceptible from the surface. The ground feels solid. The horizon feels fixed. The only evidence of the spin available without instruments is the slow arc of the sun across the sky each day, and the rotation of the stars through the night. And for most of human history, those movements were interpreted as the sky moving around a stationary Earth, rather than as an Earth rotating beneath a stationary sky. The correction took a long time to accept, even after the evidence for it was clear. Now go out one level. The Sun. Our star is a G-type main sequence star, which sounds like a bureaucratic classification and essentially is. It means the Sun is a fairly average star in terms of size, temperature, and luminosity. It is not particularly large. It is not particularly bright by the standards of the galaxy. It is not young, having formed about 4.6 billion years ago, roughly a third of the age of the universe, from a collapsing cloud of gas and dust in one of the Milky Way's spiral arms. It will continue fusing hydrogen in its core for approximately another 5 billion years before it exhausts its fuel, expands into a red giant, and eventually collapses into a white dwarf. From the Sun's perspective, which is to say, from the perspective of nuclear physics operating on stellar timescales, the current moment is middle age. The Sun is not stationary. Nothing in the galaxy is stationary. The Sun orbits the center of the Milky Way at roughly 450,000 miles per hour, and one complete orbit takes approximately 230 million years. Astronomers call this period a galactic year, or sometimes a cosmic year, and using it as a unit of time produces a way of looking at Earth history that feels genuinely different from the familiar geological timescale. In galactic years, the Earth is about 20 years old. The Sun formed roughly 20 galactic years ago. The oldest stars in the Milky Way are closer to 50 galactic years old. The universe itself is about 60 galactic years old. Complex animal life on Earth, the Cambrian explosion and everything that followed, began roughly 2 galactic years ago. The entire recorded history of human civilization, from the first writing systems in Mesopotamia to this moment, occupies less than 1/10,000th of a galactic year, less than 2 weeks in galactic time. The dinosaurs appeared about 1 galactic year ago and were gone half a galactic year later. Perspective of this kind does something to the way a story feels. It does not make human things less real or less important. It just makes the scale of the universe available as a felt thing rather than an abstract number. And felt scales change the emotional texture of everything that happens within them. Now go out another level. The Milky Way itself. The Milky Way is a barred spiral galaxy. It has a central bar of stars, a dense bulge around that bar, and several spiral arms extending outward from the ends of the bar like water thrown from a spinning wheel. The Sun sits in one of those arms, the Orion Arm, about 26,000 light-years from the galactic center. Not at the center, not at the edge, but somewhere in the middle distance, in a relatively quiet stretch of the galaxy, away from the most active star-forming regions and the denser central bulge. The total diameter of the Milky Way is roughly 100,000 light-years. Though its outer edges are diffuse, and the definition of where the galaxy ends is somewhat a matter of convention, it contains somewhere between 200 billion and 400 billion stars. It has a supermassive black hole at its center, Sagittarius R star, with a mass of about 4 million times the mass of our Sun. That black hole is currently in a quiet phase, consuming very little material and emitting little radiation. It has not always been quiet. Evidence suggests it was considerably more active in the past, and structures called the Fermi bubbles, vast lobes of high-energy gas extending above and below the galactic plane, may be remnants of an earlier period of intense activity at the galactic center. The Milky Way is ancient, but it has not always looked the way it does now. It has grown over billions of years by pulling in smaller galaxies and absorbing their stars. Evidence of those ancient mergers can still be read in the motions of certain stellar streams. Ribbons of stars moving through the galaxy at angles inconsistent with normal disk rotation. The ghostly remnants of galaxies consumed long before the Sun formed. The Milky Way we inhabit today is the product of a long history of collisions, mergers, and accretion, a history written not in visible scars but in the subtle statistical signatures of stellar velocity distributions. And the Milky Way, like every other galaxy in the universe, is not standing still. It has its own motion, its own peculiar velocity, added on top of whatever motion the expansion of the universe imparts to it. That peculiar velocity, the one measured by astronomers analyzing the asymmetry of the cosmic microwave background, is roughly 600 kilometers per second in the direction of Centaurus. The origin of that motion, the gravitational landscape that produces that slope, is the central mystery of this story. But before we follow that mystery to its resolution, there is one more layer of the familiar address to lay down, one more level of structure between the Milky Way and the vast basin that eventually comes to contain it. The Milky Way is not alone. It never has been. For billions of years. It has been part of a small, gravitationally bound family of galaxies that shares a common neighborhood in the cosmos. Understanding that family, understanding what it means for galaxies to be bound to one another, and why that binding matters, is what makes everything that comes after it comprehensible. The family has a name. It is called the local group, and it is, in the full context of this story, the smallest unit of structure that will survive intact into the deep future of the universe, the inner sanctum of a home whose outer walls are already, very slowly, dissolving. The local group is not large by the standards of what we will eventually be talking about. It spans roughly 10 million light-years from one side to the other, which sounds enormous until you place it next to the 520 million light-year basin that eventually contains it. In that comparison, the local group is a small town at the edge of a continent, quiet and self-contained, with its own internal dynamics and its own history, mostly unaware of how vast the territory it belongs to actually is. The group has roughly 80 known members, though the count shifts occasionally as astronomers identify new dwarf galaxies at its periphery, faint and small and easily missed. The vast majority of those 80 members are dwarf galaxies, small, irregular or elliptical systems containing anywhere from a few million to a few billion stars. They orbit around the two dominant members the way moons orbit planets, or the way smaller settlements cluster around a major city in a region without the population to support a second major centre. The two dominant members are the Milky Way and Andromeda. Andromeda, catalogued as Messier 31, is the largest galaxy in the local group. It is a spiral galaxy, somewhat larger than the Milky Way, containing an estimated trillion stars compared to our galaxy's 200 to 400 billion. It sits about 2.5 million light-years from the Milky Way, close enough that on a moonless night under a dark sky, you can see it with the naked eye as a faint, elongated smear in the constellation that shares its name. The light you see when you look at Andromeda tonight left that galaxy 2.5 million years ago. The ancestors of our species were just beginning to make stone tools when those photons began their journey toward your eyes. Andromeda is approaching us. At roughly 70 miles per second, Andromeda and the Milky Way are falling toward each other under their mutual gravitational attraction, and in approximately 4.5 billion years they will collide. The word collide is technically accurate but emotionally misleading, because what it conjures, two solid objects smashing into each other with violent and immediate consequences, is almost the opposite of what will actually happen. Stars are so widely spaced within galaxies that the probability of any individual star in the Milky Way directly hitting any individual star in Andromeda during the entire merger is essentially zero. The space between stars, even inside galaxies that appear dense to our eyes, is vast, beyond easy comprehension. What will happen instead is a gravitational restructuring that unfolds over hundreds of millions of years. The two galaxies will first pass through each other, their disk structures distorting as tidal forces reshape their stellar orbits. Long tidal tails of stars will be flung outward into intergalactic space. Then the galaxies will swing back toward each other and interpenetrate again. And again, each pass will be less distinct than the last, the two spirals gradually losing their separate identities, their stars mixing into new orbital configurations, until eventually the process settles into a single large elliptical galaxy. Astronomers have already given this future galaxy a name: Milky. It is not a glamorous name, but it is honest about what it represents. The product of two spirals that have merged into something new. Our Sun will almost certainly survive the process, though it will likely end up in a completely different position within the merged galaxy than it occupies today. Any planets orbiting the Sun at that point will continue to orbit it. The merger is a galactic scale event, not a stellar one. From the surface of a planet, the night sky would change dramatically over millions of years, the approaching structure of Andromeda growing larger and eventually dominating the sky before the two galaxies began their interpenetration. But no single dramatic catastrophe would mark the merger for any individual planetary system. The local group also includes Triangulum, a smaller spiral galaxy about 3 million light-years away, and a large collection of dwarf satellites, the Magellanic Clouds. The two irregular dwarf galaxies visible from the southern hemisphere as detached portions of the Milky Way are among the most studied. The large Magellanic Cloud sits about 160,000 light-years away, and is close enough that its individual stars can be resolved with modest telescopes. In 1987, a supernova exploded in the large Magellanic Cloud that was visible to the naked eye from the southern hemisphere, the closest naked eye supernova since the year 1604, and astronomers around the world scrambled to point every available instrument at it. It was a reminder that the local group is close enough to be our laboratory, not just our neighborhood. The local group is gravitationally bound. This is the most important thing about it in the context of the story we are telling. The galaxies within it will not be pulled apart by the expansion of the universe. They are held together by their mutual gravitational attraction, which at their separations and masses is strong enough to overcome the expanding tendency of space. In the far future, when the accelerating expansion of the universe has carried every galaxy outside the local group beyond the cosmological horizon, when the universe has become unimaginably emptier and darker, the local group will still be here, possibly merged into a single large galaxy by then, certainly changed beyond recognition from its current form. But here, together, bound, this makes the local group the innermost core of our cosmic address, the part of the address that will endure. But the local group does not exist in isolation. It sits within a broader region of the universe where other groups and clusters of galaxies are close enough to influence one another, where the gravitational landscape has a texture and a shape that goes well beyond anything the local group's internal dynamics can explain. And at the center of that broader region, 65 million light-years away, sits one of the most massive concentrations of galaxies in our cosmic neighborhood. Its gravitational whisper has been shaping the motions of everything around it, including the local group, for billions of years. Its presence was known for decades before anyone understood the full context it was part of, and following that whisper outward, tracing it to its source, and then beyond that source to the even larger structure that contains it, is the next step in reading the address we are trying to write. The whisper comes from Virgo, and Virgo, it turns out, is not the end of the story. It is the beginning of it. 65 million light-years is a distance that resists emotional comprehension. You can write the number down. You can say it out loud. You can compare it to smaller distances and note that it is larger by a factor that makes the comparison feel meaningless. But the full weight of 65 million light-years does not land in the way that distances on human scales land. It belongs to a different category of experience, one that the human nervous system did not evolve to process, because nothing in the environment of our ancestors required processing it. One way to make it real, or at least more real, is to think about time. The light reaching your eyes tonight from the Virgo cluster left those galaxies 65 million years ago. At that moment, the most recent mass extinction in Earth's history had just occurred. A rock roughly 6 miles in diameter had struck the shallow sea, covering what is now the Yucatan Peninsula. releasing energy so far beyond any human frame of reference that describing it numerically does not help. The impact winter that followed killed approximately 3/4 of all species on Earth, including every non-avian dinosaur. The world those photons left behind was one in which the dominant large animals had just been eliminated, in which the small, nocturnal, warm-blooded creatures that had spent the previous 150 million years living in the margins were beginning, cautiously, to move into the ecological spaces left vacant by the extinction. Those photons have been crossing the universe ever since, through the entire age of mammals, through the rise and spread of primates, through the emergence of our genus, our species, our civilizations, our science. They were already more than 64 million years into their journey when the first human being looked up at the night sky and wondered what was there. And tonight, after all of that, they reach a telescope, or an eye, on a small planet in the outer arm of a spiral galaxy, and the Virgo cluster becomes, for a moment, observable. What those photons reveal is something extraordinary. The Virgo cluster is the largest concentration of galaxies in our immediate cosmic neighborhood. It contains somewhere between 1,300 and 2,000 galaxies, depending on where you draw its boundaries, packed into a region roughly 8 million light-years across. Its mass is difficult to measure precisely, but estimates place it in the range of several 100 trillion times the mass of the Sun. At its core sit several giant elliptical galaxies, enormous featureless spheroids of stars that represent the endpoints of galactic evolution, systems that have consumed their gas and stopped forming new stars, and settled into a slow aging process that will continue for billions of years. The largest of these central ellipticals, Messier 87, is one of the most studied galaxies in the sky. It contains roughly 1 trillion stars. At its center sits a supermassive black hole with a mass of 6.5 billion suns, a number so large that the black hole's event horizon, the boundary beyond which nothing can escape, is larger than our entire solar system. In April of 2019, the Event Horizon Telescope collaboration released the first direct image of a black hole shadow, and the shadow they imaged was the one at the center of Messier 87. A network of radio telescopes spread across the entire Earth, working together as a single instrument the size of a planet, produced a blurry orange ring that became one of the most widely shared scientific images in history. The Virgo cluster matters for our story not just because of its size or the drama of its central galaxies, but because of its gravitational influence on everything around it. The Milky Way, the local group, and a broad collection of other galaxy groups spread across tens of millions of light-years in every direction are all, to varying degrees, being pulled toward the Virgo cluster. This influence is real and measurable. The peculiar velocity of the local group includes a component directed toward Virgo, a contribution from the cluster's gravity that adds to the overall flow we have been discussing. For decades, astronomers grouped the Milky Way, the local group, and the surrounding region of galaxy groups, together with the Virgo cluster itself under a common label. They called it the Virgo supercluster, or sometimes the local supercluster. The implication of that name was that we lived inside a coherent structure centered on Virgo, something analogous to a cluster but larger. A supercluster, in the literal sense of a cluster of clusters. That description captured something real. The galaxies in the region around Virgo are not randomly distributed. They show a preference for a flattened, sheet-like distribution aligned with the plane of the local supercluster. The Virgo cluster sits near the center of that distribution. The local group sits near the edge. The overall arrangement reflects the influence of Virgo's gravity on the organization of matter across tens of millions of light-years. But the description also obscured something important, a distinction that would turn out to matter enormously when astronomers began asking more precise questions about what kind of thing a supercluster actually is. A galaxy cluster is gravitationally bound. Its members cannot escape. They orbit the cluster's center of mass. They interact gravitationally, and they will eventually merge into a single larger object over billions of years. The cluster is, in a dynamical sense, a real and persistent structure. It will still be there, in some form, long after most of the rest of the universe has changed beyond recognition. A supercluster, as the term was traditionally used, is not bound in this sense. The expansion of the universe, and particularly the accelerating expansion driven by dark energy, is more than strong enough to overcome the gravitational attraction between galaxy clusters separated by tens of millions of light years. The Virgo cluster and the local group are not going to fall together and merge. The expansion will see to that. They are associated in the sense that they are part of the same overdense region of the universe, part of the same large-scale structure, part of the same gravitational neighborhood. But they are not bound into a single system the way the stars within a galaxy are bound, or the galaxies within a cluster. This distinction matters because it means that the concept of a supercluster, as it was being used in the 1980s and 1990s, he was doing two different jobs simultaneously and doing neither of them with full precision. It was describing an observed concentration of galaxies, which is one thing, and it was implying a coherent physical structure, which is something else. The concentration was real. The coherence was questionable. What astronomers needed, and what the field had not yet developed fully when the Virgo supercluster was being mapped, was a definition of large-scale structure that was grounded in dynamics rather than density, a definition based not on where galaxies are but on what they are doing, on the gravitational relationships that actually connect them, rather than the spatial proximity that makes them appear associated. The Virgo cluster was a landmark. It was a massive, unmistakable gravitational presence that had been shaping the local universe for billions of years. But it was not the center of the largest coherent structure in the neighborhood. It was just the most visible part of a much larger pattern, a major node in a flow field whose full extent had not yet been mapped. Mapping that flow field, understanding the basin that the Virgo cluster itself belongs to, along with everything around it, required following the motions of galaxies outward past Virgo, past the boundaries of the traditional local supercluster, into a region of the sky that was becoming increasingly difficult to observe as the galactic plane of the Milky Way rose up to block the view. Because the flow was pointing somewhere specific, the data was increasingly clear about that, and where it was pointing, toward a region of space in the direction of the constellation Centaurus and somewhat beyond, was almost precisely the worst possible location for optical astronomers trying to look through the plane of their own galaxy. The whisper from Virgo was real, but Virgo was whispering about something larger than itself, something that the maps of the time could not yet show, because the galaxy we lived in was standing in the way. Science rarely announces its most important discoveries cleanly. More often, they arrive sideways, buried in a table of numbers that does not quite work, or hiding in a residual after everything explainable has been subtracted away, or showing up in the difference between what a model predicts and what the instruments actually measure. The discovery that eventually led to Laniakea was like this. It did not begin with a moment of inspiration or a dramatic observation at a telescope. It began with a number that kept coming out wrong. The number was the peculiar velocity of the Milky Way. By the late 1970s, the measurement of the cosmic microwave background asymmetry had established that the Milky Way was moving at roughly 600 kilometers per second relative to the frame of the early universe. This was a clean, well-established observational result. The question it raised, and the question that would drive a decade of increasingly intense work, was what was causing it. 600 kilometers per second is a lot of motion. To put it in human terms, at that speed you could travel from the Earth to the Moon in about 11 minutes. In astronomical terms, it represents a significant peculiar velocity, one that implies a substantial gravitational influence from somewhere. The known structures in the local universe at the time, the local group, the Virgo cluster, a few other nearby clusters, could account for some fraction of that velocity when their gravitational pulls were calculated and added together. But not all of it. The numbers did not close. There was a residual, a component of the Milky Way's motion that pointed toward a region of the sky where no sufficiently massive known structure existed. Something was missing from the map. A group of astronomers who became informally known as the Seven Samurai set out in the mid-1980s to measure peculiar velocities across a wide swath of the sky. With enough precision to identify the source of the flow, the team included Donald Lyndon Bell, Sandra Faber, David Burstein, Roger Davies, Alan Dressler, Roberto Terlevich, and Gary Wagner. They used a technique involving elliptical galaxies, exploiting a relationship between the velocities of stars within those galaxies and the galaxy's intrinsic luminosities to estimate distances, and then comparing those distances to the distances implied by the galaxy's redshifts to extract peculiar velocities. The work was painstaking. Each galaxy required substantial telescope time to obtain a spectrum of sufficient quality. The analysis involved careful calibration and cross-checking to ensure that systematic errors were not masquerading as physical signals. The team spent years accumulating a sample large enough to draw meaningful conclusions. What they found confirmed and extended what the CMB asymmetry had suggested. The galaxies they measured were not moving randomly. They were flowing in a coherent, organized pattern toward a region of the sky in the direction of the southern constellation Centaurus. The flow extended across hundreds of millions of light-years in every direction, drawing in galaxies far beyond the Virgo cluster, far beyond the traditional boundaries of the local supercluster, and the mass concentration driving that flow was not visible in any existing catalogue. In their 1987 paper, the Seven Samurai coined the term that would define the mystery for the next several decades. They called the implied mass concentration the Great Attractor. The name was chosen carefully. It was not a claim about the physical nature of the object, not an assertion that some single thing of enormous mass sat at a specific point in space. It was a description of a gravitational effect, a label for the attractor at the center of a flow pattern that the data revealed, but that the maps of the time could not explain. The name stuck immediately. It had a quality that scientific terminology rarely achieves, and that, when it does, tends to indicate that the name has captured something genuinely evocative about the phenomenon, the Great Attractor, something vast and invisible, drawing the local universe toward it at speeds that dwarfed anything humans had ever moved through space. Something whose location pointed toward a region of the sky that the Milky Way's own plane was blocking from view. The scientific community's response was divided. Some researchers were excited by the implications, by the suggestion that the local universe was organized around a flow pattern of unprecedented scale. Others were skeptical, concerned that the distance measurement techniques being used were not reliable enough to establish peculiar velocities with the confidence the Seven Samurai were claiming. Spirited arguments developed at conferences. Papers appeared questioning the analysis. Competing groups produced different results from different galaxy samples. This is how science actually works. And it is worth saying so explicitly, because the popular narrative of science as a series of clean revelations misses what is most interesting about the process. The Great Attractor hypothesis was tested and argued and revised and tested again across more than a decade of work. Each new dataset either confirmed the basic picture or forced revisions to its details. The signal was robust enough to survive the skepticism, but the details changed significantly as better data accumulated. One thing that emerged from the ongoing work was that the Great Attractor, as originally conceived, was probably not a single compact mass concentration. The data was more consistent with a broad, extended region of elevated mass density, a landscape feature rather than a point source, the Hydra Centaurus supercluster complex. The collection of clusters in roughly the right direction became a leading candidate for at least part of the Great Attractor signal. But even including those structures, the numbers did not fully add up. Something additional remained unexplained, and that something was hidden behind the worst possible obstacle. The flows that the Seven Samurai and their successors were measuring all pointed toward a region of the sky that lay almost exactly along the plane of the Milky Way, the densest, dustiest, most star-crowded part of our own galaxy sat between Earth-based telescopes and whatever was causing the peculiar velocity of the local group. The optical path was blocked. The evidence was behind a wall made of stars and dust and gas that no ordinary telescope could see through. Astronomers had a name for this wall too. They called it the zone of avoidance, and the fact that the Great Attractor lay almost perfectly centered in it was, depending on your temperament, either the cruelest possible arrangement of circumstances or a genuinely fascinating demonstration of how the universe occasionally hides its most important secrets in the most inconvenient possible places. The zone of avoidance was not a new problem. Astronomers had known since the earliest systematic galaxy surveys that galaxy catalogues had a conspicuous gap along the plane of the Milky Way. Galaxies appeared to avoid that strip of sky, not because no galaxies existed behind it, but because the dust and stars of the galactic plane made them effectively invisible to optical instruments. The gap was about 20% of the full sky, a wide band centered on the Milky Way's equator, within which the extragalactic universe was essentially inaccessible to conventional observation. And right in the middle of that gap, the data said, was the most important gravitational feature in the local universe: the race to see through the zone of avoidance, to develop instruments and techniques capable of revealing what was hidden there. It would occupy astronomers for the better part of 2 decades. It would require moving beyond visible light entirely, exploiting wavelengths that the dust could not stop. It would require building new instruments and designing new surveys specifically aimed at the most obstructed part of the sky. And what those surveys eventually found there would change the picture of the Great Attractor in ways that nobody had fully anticipated, adding new structures to the gravitational landscape of the local universe, and raising new questions about the nature and extent of the flow that the 7 samurai had first identified. But before any of that could happen, the full extent and strangeness of the obstruction had to be understood. The zone of avoidance was not just an inconvenient gap in the catalogues. It was a profound limit on human knowledge of the local universe, a blind spot built into the very structure of our home. And understanding why it existed and what it concealed would require sitting with one of the most interesting ironies in the history of astronomy. The thing most responsible for blocking our view of the universe was the same thing we lived inside. There is a blind spot in your vision right now, not a metaphorical one, a literal, physical blind spot built into the anatomy of every human eye, located at the point where the optic nerve connects to the retina, and where no photoreceptive cells exist to register incoming light. Light falling on that precise location produces no signal. The brain fills the gap automatically, drawing on information from the surrounding visual field to construct an image that feels seamless and complete. You never notice the blind spot because the system concealing it works so well, but it is there. It has always been there, and for most of human history nobody knew it existed. The zone of avoidance is the blind spot of the Milky Way. It is not a gap in the universe. Galaxies exist behind it in enormous numbers, distributed through space with the same density and variety they display everywhere else. The universe does not thin out along the plane of our galaxy. It continues through that space with complete indifference to the fact that a particular civilization on a particular planet inside that galaxy has been unable to see through it. The gap is in our view, not in the territory, and like the eye's blind spot, it is created by the very structure that makes observation possible in the first place. The Milky Way is the galaxy whose gravity holds our solar system together, whose generations of dying stars produce the heavy elements that make up our bodies, whose star-forming regions gave birth to our sun 4.5 billion years ago. And it is also, in a direct and measurable way, the thing that blocked our view of the most important gravitational structure in our cosmic neighborhood. For the entire history of human observation, the physics of the obstruction is straightforward. When we look along the plane of the Milky Way, we are looking through the full thickness of the galactic disk. The disk is filled with stars, gas clouds, and most consequentially, dust. Interstellar dust grains are small particles of carbon compounds and silicate material, each one measuring a fraction of a micron across, which is smaller than the wavelength of visible light. When photons of visible light encounter these grains, they are scattered and absorbed with high efficiency, A single cloud of interstellar dust a few hundred light-years thick can dim a distant galaxy by several magnitudes, enough to push it below the detection threshold of even sensitive optical surveys. Along the galactic plane, there are not one or two such clouds between us and the extragalactic universe. There are dozens, stacked behind each other for tens of thousands of light-years, each one adding its contribution to the cumulative obscuration. The result is that the galactic plane, invisible light, is essentially opaque to extragalactic observation across a wide band of the sky. The obscuration is not uniform. It varies with direction along the plane, with some windows where the dust is thinner and galaxies can be seen at greater depths, but averaged across the full band. Roughly 20% of the entire celestial sphere is so heavily obscured that no optical survey has ever produced a reliable catalogue of galaxies through it. 20%. That is not a narrow strip at the edge of the observable sky. That is a substantial fraction of everything above you on any given night. A wide band running all the way around the sky from horizon to horizon, through which the extragalactic universe has been invisible to every optical telescope ever built on Earth. And the Great Attractor, by a combination of geometry and bad luck, sits almost perfectly centered in that band. The frustration this created for astronomers trying to understand the peculiar velocity of the Milky Way was genuine and lasting. The data pointed clearly at a region of elevated mass density, somewhere in the direction of Centaurus and somewhat beyond. The calculations required a concentration of mass large enough to accelerate the local group and everything around it to 600 kilometers per second. And the most direct path to confirming or characterizing that concentration was blocked by the plane of the galaxy we lived in. The response was to find wavelengths that the dust could not stop. Radio waves have wavelengths far longer than visible light, and they pass through interstellar dust with almost no absorption. The 21-centimeter emission line of neutral hydrogen, a radio frequency signal produced by hydrogen atoms as their electrons flip between two energy states, can be detected from galaxies behind the galactic plane as easily as from galaxies in the clearest regions of the sky, beginning in the 1980s and extending through the 1990s and beyond. Systematic radio surveys began mapping galaxy redshifts through the zone of avoidance, building catalogues of galaxies that had never appeared in any optical survey. Infrared wavelengths, somewhat longer than visible red light, also penetrate dust more effectively than optical wavelengths do, though less completely than radio waves. Infrared satellite missions, particularly the IRAS satellite in the 1980s and its successors, conducted all-sky surveys that revealed galaxy populations in the zone of avoidance, invisible to optical instruments. The 2-micron all-sky survey and the WISE mission extended this infrared coverage with improving sensitivity and resolution. X-ray emission from the hot intergalactic gas that fills massive galaxy clusters pierces through substantial columns of dust as well. X-ray satellites identified clusters in the zone of avoidance whose optical counterparts could not be seen. Each new detection was another piece of a picture that had been partially obscured for the entire history of extragalactic astronomy. What accumulated through these surveys, over the course of roughly 3 decades of persistent work, was a gradually clarifying view of what lay behind the galactic plane in the direction of the Great Attractor. The Norma cluster, sitting at roughly 220 million light-years distance near the center of the Great Attractor region, emerged as one of the most massive galaxy clusters in the local universe. Identified first through X-ray emission and then confirmed and characterized through radio and infrared observations, the Norma cluster was not alone. It sat within a broader complex of clusters and filaments that, taken together, accounted for a substantial portion of the gravitational pull the peculiar velocity data had been measuring. But the zone of avoidance had not finished producing surprises. In 2017, a team led by René Kraan-Korteweg at the University of Cape Town published a study confirming the existence of a major supercluster hiding in the zone of avoidance. At a distance of roughly 800 million light-years, the team had used the Southern African Large Telescope for optical spectroscopy of galaxies identified in radio surveys, measuring enough redshifts to establish that a significant concentration of galaxies existed in that direction at that distance. They named it the Vela Supercluster. Vela's estimated mass placed it in a category comparable to the Shapley Supercluster, which had long been considered the largest and most influential mass concentration in the local universe beyond the Great Attractor region. The discovery indicated that the gravitational landscape pulling the Milky Way through space included a major contributor that every previous survey had missed entirely. Not because it was too faint or too distant, but because it sat behind the plane of our own galaxy, the zone of avoidance. Even after decades of multi-wavelength surveys, was still concealing important structures. The blind spot had been reduced, illuminated in patches, partially mapped through wavelengths that dust could not block, but it had not been eliminated. The surveys were ongoing, better radio arrays, more sensitive infrared instruments, and deeper spectroscopic follow-up continued adding detail to regions that had previously been blank. The most important lesson of the zone of avoidance was not about any specific structure found within it. It was about the nature of maps and the nature of knowledge. Every map is a record of what was visible at the time it was made. The territories beyond the edges of the map are not empty. They are simply uncharted. And the most consequential uncharted territories are sometimes not the ones farthest from home, but the ones closest, the ones hidden by the very walls of the place you live in. For all of human history, the Milky Way has been both our home and our blind spot. We have been inside Laniakea for billions of years without knowing it, flowing toward an attractor we could not see, embedded in a basin whose boundary was partially hidden behind our own galaxy's plane. The address existed before we could read it. The current was running before we had instruments sensitive enough to feel it. The zone of avoidance was not a problem that got solved. It was a problem that got worked on, and continues to be worked on, with each new survey revealing structures that previous surveys could not see. That ongoing work is part of what makes the map of Laniakea a living document rather than a finished product. A boundary drawn in the current data that will shift and sharpen as the data improves. Position alone does not tell you where something belongs. A single galaxy, observed through a telescope, gives you a location in the sky and a redshift that implies a distance. It tells you where the galaxy appears to be. What it does not tell you is what the galaxy is doing, which way it is moving relative to the smooth expansion of the universe, whether it is falling toward a cluster or drifting away from one, whether the large-scale flow in its neighborhood is pulling it toward the same basin as the Milky Way, or toward a completely different attractor on the other side of a gravitational divide. Position is a snapshot. Motion is a story. This distinction between snapshot and story is the conceptual foundation of the method that eventually produced Laniakea. The method was not invented overnight. It developed over decades of incremental improvement in distance measurement techniques, computational tools, and theoretical frameworks, and the astronomer who invested more years in building the observational foundation for it than perhaps anyone else is Brent Tully, who has been working on galaxy distances and large-scale structure from the Institute for Astronomy at the University of Hawaii since the 1970s. Tully is not the kind of scientist who appears frequently in popular accounts of astronomical discovery. He has not made single dramatic observations that generate press releases. What he has done is harder, slower, and ultimately more consequential. He has spent decades building catalogues, measuring the distances of individual galaxies one by one, accumulating data points across thousands of objects spread across hundreds of millions of light-years, improving the techniques used for each measurement, extending the coverage with each new survey, and developing the analytical methods needed to extract the gravitational landscape from the accumulated data. The project that most fully expresses this long-term effort is Cosmic Flows. Cosmic Flows began as a modest catalogue of a few thousand galaxy distances and peculiar velocities, published in 2008. Each subsequent iteration expanded both the number of galaxies and the sophistication of the analysis. Cosmic Flows, 2, the dataset used for the Laniakea paper, contained distance measurements for roughly 8,000 galaxies. Cosmic Flows, 3 extended the catalogue to nearly 18,000. Cosmic Flows, 4, The most recent major release at the time of this writing incorporated distance measurements for nearly 60,000 galaxies, extending the reach and improving the resolution of the peculiar velocity map across a much larger volume of the local universe. The core measurement behind every entry in the cosmic flow's catalogues is the peculiar velocity of a galaxy. Getting that requires two independent measurements of the same quantity. First, the redshift of the galaxy, which gives a recession velocity. Apply the Hubble law to that velocity and you get a distance. The distance the galaxy would be at if it were simply riding the Hubble flow with no additional motion. Second, an independent distance measurement using a method that does not depend on redshift, the Tully-Fisher relation, which Tully co-developed with Richard Fisher in the 1970s, has been the primary tool for this with spiral galaxies. The relation connects the rotational speed of a spiral galaxy, measured from the width of its emission lines, to its intrinsic luminosity. More massive galaxies rotate faster and shine more brightly, and the relationship between these two quantities is tight enough to use as a distance indicator. Measure how fast the galaxy rotates. Calculate from that how bright it should intrinsically be. Compare that intrinsic brightness to its apparent brightness in the sky. The difference gives you the distance. Compare that distance to the Hubble distance implied by the redshift. The difference between the two distances, expressed as a velocity, is the peculiar velocity. Any individual measurement of this kind carries uncertainty. The Tully-Fisher relation has scatter, meaning individual galaxies deviate from it in ways that introduce error into any single distance estimate. But the law of large numbers is forgiving. With thousands of galaxies distributed across the sky, the random errors average out across the full sample, and the systematic signal, the coherent peculiar velocity field driven by the actual gravitational landscape, emerges from the noise. The computational side of extracting the gravitational landscape from the peculiar velocity data was developed primarily by Yehuda Hoffman at the Hebrew University of Jerusalem. The algorithm he and his collaborators refined for the Laniakea analysis uses the observed velocities as constraints and reconstructs the three-dimensional density and velocity field across the surveyed volume. The reconstruction fills in unobserved regions, including parts of the zone of avoidance, using statistical assumptions about the expected structure of the cosmic density field based on cosmological models. The result is a smooth, continuous, three-dimensional map of the peculiar velocity flow across the local universe, out to several 100 million light-years. From that flow map, Tully and his team asked a specific question. For each point in the reconstructed volume, which direction does the local flow point? If you were a galaxy at that position, with no external information about where you were, the direction of the flow would tell you which attractor basin you were in. Follow the flow inward and you reach the attractor. Find the surface where the flow reverses direction and you have found the boundary. The mathematical formalism for this comes from physical geography. On the surface of the Earth, you can define drainage basins by tracing the direction of steepest descent from every point. Every point on the land surface drains toward one of the world's ocean basins, and the boundaries between basins are the watershed divides, where the slope changes from favouring one drainage direction to favouring another. The same construction works in the three-dimensional gravitational potential field of the local universe. Every point in space has a direction in which the peculiar velocity flow moves. Follow that direction and you reach an attractor. The boundaries between different attractors define the supercluster basins. When Tully, Courtois, Hoffman, and Pomerade applied this construction to the cosmic flows, two data. The basin that emerged around the Great Attractor region was larger than any previous supercluster definition had suggested. It encompassed roughly 100,000 galaxies across a volume 520 million light-years in diameter. The Milky Way sat within it, near the outer edge of a sheet of galaxies that included the local group and extended toward the Virgo cluster and beyond. The team needed a name for the basin. Tully turned to colleagues at the University of Hawaii and organized a naming process that drew on the Hawaiian language and the navigational tradition associated with it. The winning proposal came from a student who offered two words: Lani. meaning sky or heaven; Akea, meaning spacious or immeasurable; Laniakea. The choice was not arbitrary. The Hawaiian navigational tradition, one of the most sophisticated wayfinding systems ever developed by any human culture, is built on reading motion. Polynesian navigators found their positions across the open Pacific not by fixing themselves to a static grid, but by understanding the flows around them, the arc of stars, the direction of ocean swells, the behavior of clouds and birds and wind. They knew where they were because they understood how things moved. The method that found Laniakea was the same method applied to the cosmos. Read the motion of the galaxies. Follow the flows. Find where they converge. Draw the boundary where they diverge. That is the basin. That is the structure. That is the largest address we have been able to write for ourselves. The name honoured that method, and the people who had been practicing it, on a different ocean and at a different scale, for thousands of years before the telescopes arrived. September 3rd, 2014. On that morning, a paper appeared in the journal Nature under the title The Laniakea Supercluster of Galaxies. 4 authors. 4 pages in its published form. Supplementary material extending the technical details for specialists who needed them. By the compressed standards of modern scientific publishing, it was a concise document. By the standards of what it was saying, it was one of the most significant cosmological papers published in the 21st century. The paper described a supercluster, but not a supercluster in the loose, density-based sense that the word had been used for decades. A supercluster defined by its flow basin, a region of space 520 million light-years across, containing roughly 100,000 galaxies, within which all peculiar velocity flows, after the Hubble expansion was subtracted out, converged toward a common gravitational center. The basin had a boundary drawn not by human judgment or density threshold, but by the physics of the gravitational field itself, the surface in three-dimensional space where the direction of galactic motion changed from inward to outward, from falling toward this attractor to falling toward a different one. The Milky Way sat within that basin, near the edge of one of its outer sheets, far from the central concentration, but unambiguously inside the boundary, part of the flow, part of the structure. The paper came with a visualization, and the visualization changed everything about how the discovery landed in the public imagination. Daniel Pomerade, the scientific visualization specialist who was one of the 4 authors, had spent months converting the three-dimensional flow field reconstructed from the cosmic flows to data into something a human brain could hold. What he produced was a rendering of remarkable clarity and beauty, streams of glowing lines moving through dark space, each stream representing the local peculiar velocity at a point in the reconstructed volume, coloured and directed so that the eye could follow the motion. From the outer regions of the structure, the streams flowed inward, converging toward the dense central region the way rivers converge toward a delta. The boundary of the basin was visible as the surface where the streams reversed direction, where flows that had been pointing inward suddenly turned away and began moving toward neighbouring structures. In one region of the visualization, a small marker indicated the position of the Milky Way. When the paper and visualization were released simultaneously on September 3rd, something happened that scientific papers about large-scale structure rarely produce. The visualization spread, through science news outlets initially, then through general media, then through social platforms where people who had never previously thought about peculiar velocities or gravitational basins shared it with their networks. The video of the three-dimensional flow field was watched millions of times within days of its release. It was shown on television news broadcasts in multiple countries. It appeared in newspapers alongside stories that struggled, with varying degrees of success, to explain what exactly people were looking at. Part of what drove the response was the quality of the visualization itself. Pomerade's rendering was genuinely striking, but something deeper was operating too. Something that explains why this particular cosmological result connected with people in a way that previous large-scale structure discoveries had not. The visualization showed people where they were, not in the abstract way that a diagram of the solar system's position in the Milky Way shows you where you are, providing a sense of scale without a sense of context. The Laniakea visualization showed the Milky Way as a participant in something organized, a small marker within a vast structured flow, embedded in a basin that had a shape and a center and a boundary. It made the relationship between the Milky Way and its larger cosmic context not just intellectually available but visually immediate. You could look at the image and feel, in a way that numbers in a table cannot produce, the sense of being somewhere specific within a very large thing. That response, that felt sense of location within a larger structure, is precisely what the name was meant to evoke. Tully had turned to colleagues at the University of Hawaii when it came time to choose a name for the basin. A process was organized among students at the Institute for Astronomy, and the winning proposal came from a student who drew on the Hawaiian language, Lani, meaning sky or heaven, Akea, meaning spacious or immeasurable, together Laniakea, immeasurable heaven. The choice was deliberate on multiple levels. The University of Hawaii played a central role in the research. The Hawaiian Islands, sitting in the middle of the Pacific Ocean, were themselves the product of one of the greatest navigational achievements in human history. The Polynesian settlement of the Pacific that brought the ancestors of native Hawaiians to these islands roughly 1,500 years ago, and the navigational tradition that made that settlement possible was built, at its foundation, on exactly the same insight that the cosmic flows method embodied. You do not find your place by measuring fixed positions. You find it by reading how things move around you. The Hawaiian Star Compass, the system by which Polynesian navigators tracked the rising and setting points of more than 100 stars to maintain heading across thousands of miles of open ocean, is a map of motion. The ocean swells that experienced navigators felt through the hulls of their canoes to maintain bearing on overcast nights are a map of motion. The flight patterns of birds returning to roost in the evening, used to identify the direction of land beyond the visible horizon, are a map of motion. Polynesian navigation is, in its essence, a practice of reading flows and using those flows to locate yourself within a dynamic system. Brent Tully and his collaborators had done the same thing at a scale that would have been literally unimaginable to those canoe navigators. They had read the flows of 100,000 galaxies moving through the gravitational landscape of the local universe, and used those flows to identify the basin the Milky Way was part of. They had found the watershed divide that separated Laniakea from neighbouring basins, and drawn its boundary in three-dimensional space. They had produced a map, not of positions, but of motion. Laniakea. The name honoured that. Now, here is what Laniakea actually looks like in physical terms, as best as the current data allows us to describe it. The structure spans 520 million light-years from its outermost extent in one direction to its outermost extent in another. This is not a diameter in the strict geometric sense, because Laniakea is not a sphere. It is an irregular, elongated structure, wider in some directions than others, reflecting the particular topology of the dark matter web in the local universe. The long axis of the structure runs roughly in the direction of the Great Attractor region toward one end, and outward toward the Perseus-Pisces supercluster boundary on the other. Within the basin, galaxies are organized into sheets, filaments, and clusters. The Great Attractor region near the center, associated primarily with the Norma cluster and the broader Hydra Centaurus supercluster complex, represents the densest concentration of mass within Laniakea, the gravitational center toward which the inward flows are directed. The Virgo cluster, which sits at roughly 65 million light-years from the Milky Way, is part of Laniakea, connected to the broader structure through a sheet of galaxies that includes the local group. Numerous other clusters and groups are distributed throughout the basin. The Milky Way itself sits in a region called the Milky Way sheet, or sometimes the local sheet, a flattened concentration of galaxies that includes the local group and several neighbouring groups arranged roughly in a plane. This sheet is itself part of a larger structure, one of several sheets and filaments that feed into the central concentration of Laniakea. The Milky Way is not at the centre of Laniakea. It is not even in a particularly prominent location within it. It sits near the edge of a sheet in the outer reaches of the basin, a small town on the margin of a continent rather than a city at its heart. The total mass contained within Laniakea is estimated at roughly 10 to the power of 17 solar masses. Writing out what that means in familiar units does not help much. It is 100 million billion times the mass of our Sun. It is several 100 trillion times the mass of the Milky Way. It is the combined mass of 100,000 galaxies, plus all the dark matter and hot gas and other material distributed throughout the basin between them. And Laniakea is not the largest structure in the observable universe. There are other supercluster basins of comparable size elsewhere in the cosmos. The observable universe, the region of space from which light has had time to reach us since the Big Bang, is roughly 93 billion light-years in diameter. Laniakea, at 520 million light-years across, is a large but not exceptional node in the cosmic web at the scale of the observable universe. It is our node, the one we are part of, the largest unit of structure to which we currently belong. But belonging to it raises a question that the paper itself addressed only briefly, and that most popular accounts of the discovery set aside entirely. What does it mean to belong to something defined by motion? What kind of structure is Laniakea? Exactly. If its boundary is drawn by a flow field rather than by gravitational binding, is it a real thing, in the way a galaxy or a cluster is a real thing? Or is it a useful organizational concept that captures something true about the current state of the universe without quite being a physical object? The question is not pedantic. It goes to the heart of what Laniakea is, and what it means to call it home, and sitting with it honestly, working through what the science actually says rather than what the headlines imply, reveals something about the nature of cosmic structure that is more interesting and more philosophically rich than the simple version of the story. The simple version says we live in a supercluster called Laniakea. Full stop. The full version says something considerably stranger, and considerably more beautiful. Somewhere in the Rocky Mountains, there is a spot you could stand, where the rain falling on your left shoulder would eventually reach the Pacific Ocean, and the rain falling on your right shoulder would eventually reach the Gulf of Mexico. Not today. Not quickly. The water would spend years moving through soil and groundwater and streams and rivers before completing its journey. But the journey it took, the ocean it ultimately reached, would be determined entirely by which side of an invisible line it fell on. Lines like this run across every continent on Earth. They are called watershed divides, or drainage divides, and they are among the most consequential geographic features that exist, shaping the distribution of water across entire regions, determining which communities share river systems, defining the drainage architecture of landscapes across hundreds of thousands of square miles. Stand on the Continental Divide in Colorado and it looks like a mountain ridge. There is no sign, no visible line painted across the ground, no physical barrier of any kind. It is just the place where the terrain slopes one way rather than another. The water does not know it is crossing a divide. It simply flows downhill, following the path of least resistance, and the geometry of the terrain determines where it ends up. The boundary of Laniakea is a divide of exactly this kind. It is a surface in three-dimensional space where the direction of the gravitational landscape changes, where the local peculiar velocity flow shifts from pointing toward the Great Attractor basin to pointing toward a different basin entirely. Pierce's Pisces on one side, Coma on another. The boundary runs through the surrounding universe in 3 dimensions the way the Continental Divide runs across the Rocky Mountains in 2, and it was mapped not by looking at the positions of galaxies along it, but by calculating, from the flow field data, the surface where the flow direction reversed. On one side of the boundary, galaxies are flowing, on net, toward the attractor at the heart of Laniakea. On the other side, they are flowing toward a different attractor. The galaxies sitting right on the boundary are at a kind of gravitational equilibrium. equally pulled by the basins on either side. Their peculiar velocities close to zero relative to the overall flow field. They are, in the geographic metaphor, standing on the divide, with neither ocean having a decisive claim on the water falling there. This picture of Laniakea as a drainage basin rather than a walled enclosure resolves a question that the discovery raised for many people who encountered it. The question was, if we live inside Laniakea, why do we not feel it? Why does nothing about the experience of existing on Earth communicate membership in a 520 million light-year structure? The answer is that membership in a drainage basin is not something you feel in the sense of pressure or confinement. It is a geometric fact about which direction you are flowing. The Milky Way is inside Laniakea because its peculiar velocity, right now, in this epoch of the universe, points toward the Great Attractor rather than away from it. That is the entire content of membership. There is no wall keeping the Milky Way in. There is no force pressing it toward the center the way a container presses against its contents. There is only a gravitational landscape that slopes, very gently, in one direction rather than another, across the enormous volume of space the Milky Way inhabits. You are inside Laniakea for the same reason water falling on the eastern slope of the Rockies ends up in the Gulf of Mexico rather than the Pacific. Not because a wall stops it from going the other way, because the ground slopes in a particular direction at the point where it lands. Now, the watershed metaphor illuminates the nature of Laniakea's boundary, but it also points towards something important about what Laniakea is not. A drainage basin on Earth is a permanent geographic feature. The Rocky Mountains will be there for millions of years. The direction in which water flows from them will not change meaningfully on any timescale relevant to human civilization. The watershed is fixed by the stable topography of a solid planet. Laniakea is not fixed. The gravitational landscape of the local universe is not stable in the way the Rocky Mountains are stable. It is evolving, dark energy, the mysterious component of the universe that is driving the accelerating expansion of space, is changing the balance between gravitational attraction and cosmic expansion across large scales. Over billions of years, dark energy will increasingly tilt the contest between inward flow and outward expansion in favor of expansion. For galaxies that are not tightly bound to one another, the peculiar velocity flows that define Laniakea today will weaken. The galaxies near the boundary will slow their inward drift, stop, and eventually begin moving outward. The basin will shrink as its more distant members lose their connection to the central attractor. Laniakea is a feature of the universe as it exists right now. In this particular epoch, with this particular balance of forces, it was not the same structure 10 billion years ago. When the universe was younger and the gravitational landscape was organized differently, it will not be the same structure 10 billion years from now, when dark energy will have had considerably more time to stretch the space between unbound structures. This is the point where many popular accounts of Laniakea stop. They describe the basin, show the visualization, note the scale, and leave the reader with the impression that Laniakea is a permanent feature of the cosmos, a structure that will be there indefinitely, the way the Milky Way will be there indefinitely. But Laniakea is not like the Milky Way in this respect. The Milky Way is gravitationally bound. Its stars cannot escape it. Its dark matter halo will persist for trillions of years. The Milky Way will exist, in some recognizable form, long after most other things in the observable universe have changed beyond recognition. It is, in a dynamical sense, a persistent structure on time scales that include the entire future history of complex life in the cosmos. Laniakea is not gravitationally bound as a whole. The galaxies in its outer regions are not trapped. Dark energy will eventually win its contest with gravity at those scales, and carry the outer members away. The structure defined by the current flow field will dissolve over billions of years, not through any dramatic event, but through the gradual weakening of the flows as expansion overwhelms infall. And yet Laniakea is real, completely, physically, observationally real. The flows are real, the basin is real, the boundary is real, drawn by the physics of the gravitational field rather than by human convention. The motion of the Milky Way toward the Great Attractor region, the shared trajectory of 100,000 galaxies converging toward a common center, all of it is physically real and supported by direct measurement. What Laniakea is, precisely, is a dynamical structure, not a bound object, not a permanent feature, but a coherent, organized, physically meaningful pattern in the flow of the universe through its current evolutionary phase. It is real the way a weather system is real, defined by its dynamics rather than its substance, genuine and consequential while it exists, and temporary in the way that everything in the universe is ultimately temporary. A hurricane is not a permanent object. It has no rigid structure. It is defined entirely by a rotating wind pattern organized around a low-pressure center. Its boundary is drawn by meteorologists according to where the organized circulation ends. It will eventually dissipate, but while it exists, it is absolutely real. It has a center. It has boundaries. It exerts real effects on everything within and around it. Whether you are inside the storm or outside, it is a meaningful and consequential difference. Laniakea is something like a hurricane of galaxies, measured not in hours but in billions of years, spanning not hundreds of miles but hundreds of millions of light years, but organized, bounded, dynamically coherent, and real in exactly the same sense that any pattern defined by its physics rather than its matter is real. The watershed is not a wall, but that does not make it less real. It makes it a different kind of real, the kind that requires understanding dynamics rather than just positions, the kind that rewards the patience of astronomers who spent decades measuring galaxy motions one by one until the pattern became clear enough to draw. You are inside a basin defined by motion. You are part of a flow that has been running for billions of years. The watershed that places you in Laniakea rather than Perseus, Pisces or Coma is as real as any geographic feature on Earth, and as temporary as any weather system in the sky. Both things are true, and holding both of them together, without resolving the tension between them in favor of one or the other, is what it means to understand what Laniakea actually is. When you look at a map of the universe on large scales, the first thing that strikes you is not the galaxies. It is the pattern they form. Galaxies do not scatter randomly through space the way dust scatters in a sunbeam. They cluster, and those clusters connect to other clusters through long, thin filaments of galaxies stretching across tens of millions of light years. The filaments intersect at dense nodes where the galaxy concentration reaches its highest values. Between the filaments lie enormous regions where galaxies are nearly absent. Dark expanses of space, hundreds of millions of light years across that cosmologists call voids. The overall architecture looks, at large enough scales, something like the structure of a sponge, or a foam, or the network of threads in a three-dimensional spider web. Astronomers call it the cosmic web. The cosmic web is the largest organized structure in the observable universe. It is the framework within which every galaxy, every cluster, every supercluster including Laniakea exists. To understand Laniakea, to understand why it has the shape it does, and why the flows within it are organized the way they are, you have to understand what built the cosmic web in the first place. The answer is not the galaxies themselves. The galaxies are not the architects of the structure. They are the luminous traces of it, the visible markers of something much larger and almost entirely invisible. The architect is dark matter. Dark matter is a component of the universe that does not emit light, does not absorb light, and does not interact with electromagnetic radiation in any way that has been directly detected. It passes through ordinary matter with almost no interaction. Dense clouds of dark matter are drifting through your body right now, and every other body on the planet, and through the Earth itself, and they leave no detectable trace as they pass. If you tried to feel dark matter, you could not. If you tried to see it, you could not. If you tried to catch it in any instrument designed to detect electromagnetic signals, it would not register. And yet it is the dominant component of matter in the universe. Ordinary matter. the kind made of protons, neutrons, and electrons, the kind that forms stars, planets, gas clouds, people, and everything you have ever directly observed, accounts for roughly 5% of the total energy content of the universe. Dark matter accounts for roughly 27%. Dark energy, the component driving the accelerating expansion, makes up the remaining 68%. The stuff you can see, the stuff that fills every astronomy photograph ever published, is a minority constituent of the cosmos. The universe is mostly made of things that do not interact with light at all. Dark matter was not invented to explain the cosmic web. It was inferred from a completely different observation, one made by astronomer Fritz Zwicky in the 1930s. When he calculated the mass of the Coma cluster by two different methods and got wildly different answers, the mass he inferred from the motions of galaxies within the cluster was far larger than the mass he could account for from the visible galaxies alone. He concluded that most of the cluster's mass was not visible. He called it dunkel materia, dark matter. Zwicky's observation was largely set aside for decades, dismissed as a measurement error or a poorly understood systematic effect. It was not revisited seriously until the 1970s, when astronomer Vera Rubin and her collaborator Kent Ford made detailed measurements of the rotation curves of spiral galaxies and found something that contradicted every expectation based on visible mass alone. The stars in the outer regions of spiral galaxies were orbiting their galactic centers at speeds that should have been impossible, given only the visible matter distribution. The rotation curves stayed flat instead of declining with distance from the center. Exactly what you would expect if each galaxy was surrounded by a massive, extended halo of invisible matter that kept the gravitational pull high even in the outer regions where the visible stars thinned out. Rubin's rotation curves, measured across dozens of galaxies over the following years, established dark matter not as an anomaly in one peculiar cluster, but as a universal feature of galaxies. Every spiral galaxy examined had far more mass than its visible stars could account for. The invisible component was not a local curiosity. It was everywhere. Subsequent decades of observation confirmed and extended this picture. Gravitational lensing, the bending of light from distant objects by the gravity of intervening mass, allowed astronomers to map the mass distribution in galaxy clusters independently of any assumptions about the nature of the matter. The maps showed mass concentrations far more extended and far more massive than the visible galaxy distributions within the clusters. The dark matter halos were real. They were large. They dominated the total mass budget. What does all of this have to do with the cosmic web and with Laniakea? In the early universe, shortly after the Big Bang, the distribution of both ordinary matter and dark matter was nearly uniform. Nearly, but not perfectly. Quantum fluctuations during the inflationary epoch had seeded tiny density variations, regions where the matter density was fractionally higher or lower than the cosmic average. The differences were small, roughly 1 part in 100,000. But gravity is relentless. Regions that were slightly denser than average had slightly stronger gravitational pull. They attracted surrounding matter. They grew denser, which strengthened their gravity further, which attracted more matter. Dark matter drove this process more effectively than ordinary matter could have alone. For a reason rooted in atomic physics, ordinary matter in the early universe was coupled to radiation, meaning that photons and baryons, the particles making up ordinary matter, were so thoroughly mixed and interacting that the radiation pressure prevented the ordinary matter from collapsing into structures. The ordinary matter was held up by light. Dark matter experienced no such coupling. It interacted only gravitationally, which meant it could begin clumping and collapsing into structures much earlier in cosmic history, well before the ordinary matter was free to follow. The dark matter collapsed first, forming a three-dimensional network of filaments and nodes and sheets across the young universe. This network is sometimes called the dark matter scaffold, the invisible architecture within which the visible universe would later assemble. When the universe eventually cooled enough for ordinary matter to decouple from radiation and fall freely under gravity, It fell into the gravitational wells that dark matter had already carved out. Gas accumulated along the dark matter filaments. It collapsed further into dense knots at the intersections of filaments. It fragmented into clouds. The clouds collapsed into the first stars. The stars formed the first galaxies. The galaxies organized along the dark matter network into the cosmic web we observe today. The galaxies are the foam on the wave. The dark matter is the ocean. Laniakea sits within this dark matter architecture. Its shape, the elongated irregular structure of its basin, the location of its central attractor, the directions from which its inward flows approach. All of these reflect the particular topology of the dark matter web in the local universe. The Norma cluster sits where it does at the heart of the Great Attractor region because a massive dark matter concentration exists at that location. Having been growing and accumulating matter since long before the first stars formed in any of the galaxies now clustered around it, the filaments along which galaxies stream into the central concentration trace dark matter filaments that were laid down in the first billion years of cosmic history. The Milky Way sits where it sits within Laniakea because of where it ended up in the dark matter web. The solar system formed in the outer arm of the Milky Way because of the particular structure of the gas disk of the early Milky Way. That disk formed where it did because of the dark matter halo within which the galaxy assembled. The dark matter halo grew where it did because of where a seed density fluctuation existed in the primordial universe, before the first star ever shone. The chain of causation runs all the way back. The address we are tracing outward from the room where you are lying right now connects, at its deepest layer, to a quantum fluctuation in the density of the primordial plasma roughly 14 billion years ago. Everything in between is gravity doing its patient, relentless work on structures that were always going to form in approximately the places and shapes they eventually took. There is something vertiginous about following that chain. The universe does not feel as if it is operating on that timescale from where we stand, but it is, and the cosmic web is the record of that operation. Laniakea is a chapter in that record, a particular basin in a particular epoch, shaped by a dark matter architecture that was set in place long before the Milky Way existed, and that will persist, in some form, long after Laniakea as a defined structure has dissolved. The skeleton endures, the flesh is temporary, and the skeleton is dark. The universe, when mapped at large scales, turns out to be mostly nothing. Not mostly thin, not mostly sparse, mostly, in a real and measurable sense, empty. The cosmic web is a structure of contrasts, and the contrast that defines it as much as the bright filaments and dense clusters is the vast emptiness between them. Cosmologists call these empty regions voids, and by volume they dominate the observable universe, the filaments and clusters and superclusters, all the structure that maps and visualizations tend to emphasize, occupy a minority of the total volume. Most of the space in the universe is void. The local void sits just outside the local group. It is a region of below-average galaxy density, extending across tens of millions of light-years in the direction away from the Virgo cluster. The Milky Way is on its edge. If you could somehow stand outside the Milky Way and watch the flow of galaxies in the local region, you would see the local void pushing galaxies outward from its center, contributing a component of the local group's peculiar velocity that points away from the void. The Boots void, discovered in 1981 when astronomers surveying galaxy redshifts noticed an enormous and conspicuous absence of galaxies in a region of the sky in the constellation Boots, stretches across roughly 330 million light-years. When it was first reported, its existence tested the limits of what cosmological models of the time predicted was possible. A void of that size implied that the universe had been able to evacuate a region that large of most of its matter over the age of the universe, which required either that the original density fluctuation seeding the void had been unusually deep, or that the void had grown through mergers with smaller voids over cosmic time, or both. The Boots void is not unusual except in size. Voids exist throughout the observable universe, in a range of scales, from small underdensities a few tens of millions of light-years across, to enormous ones rivaling Boots, They are a fundamental feature of the cosmic web, as integral to its architecture as the filaments and clusters. A cosmic void is not simply the absence of something interesting. It is an active participant in the dynamics of the universe around it. The reason has to do with how gravity works in regions of below average density. In a region with average density, the gravitational pull in every direction roughly cancels out, and matter stays put or moves only under the influence of nearby concentrated structures. In a region of above average density, the stronger gravity pulls matter inward, causing the region to grow denser over time. In a region of below average density, the situation is the reverse. The gravitational pull from the denser regions surrounding the void is stronger than the pull from within it. Matter on the inner surface of the void is pulled outward toward the denser surrounding regions, rather than inward toward the sparse center. The void empties itself. It grows. This outward flow from voids has a formal description in cosmological terms. A void acts as a source of outward peculiar velocity for matter in its vicinity. Galaxies near a void are pushed, not by any exotic repulsive force, but by the simple geometry of being in a region where the gravitational pull from outside exceeds the gravitational pull from within. They flow outward toward the void's edges, where they pile up in the filaments and sheets that form the boundaries of the void. The void grows. The filaments become more concentrated. The contrast between the two regions deepens over time. In the framework of Laniakea and the cosmic watershed, voids play a role that is easy to underestimate. The boundary of Laniakea, the surface where inward flows toward the Great Attractor give way to flows pointing toward other attractors, is shaped not only by the distribution of mass that defines the competing attractors, it is also shaped by the voids surrounding Laniakea, whose outward flows push against the inward flows of the basin from outside. The boundary sits where the inward pull of the attractor and the outward push of the surrounding voids reach equilibrium. Change the distribution of voids and you change the shape of the boundary. In 2017, a research team, including Yehuda Hoffman, one of the Cosmic Flows collaborators who had worked on the Laniakea paper, published a study that formalized this void-driven component of peculiar velocity under the name of a repeller. The term was not intended to imply a new force or an exotic physical mechanism. It was a description of the effect of large underdense regions on the surrounding flow field. A region of significantly below average density acts, in the peculiar velocity framework, as a source of outward flow. From the perspective of galaxies in its vicinity, it repels. The specific structure they identified was large and significant enough to name. They called it the dipole repeller. The dipole repeller is a region of substantial underdensity, located roughly 600 million light-years from the Milky Way, in the direction roughly opposite to the Great Attractor region in the sky. The study argued that the motion of the local group could not be fully explained as a simple fall toward the Great Attractor and its associated mass concentrations. The motion was better understood as movement along a gradient between two poles. On one end, the gravitational pull of the large mass concentrations in the Great Attractor region and the Shapley supercluster. On the other end, the effective outward push of the dipole repeller, driving the local group away from itself and toward the attractors on the opposite side. We are not simply falling toward Laniakea's center, we are being pushed from behind as well. This two-pole picture, attraction from one direction and effective repulsion from another, describes something that is intuitively familiar at smaller scales, even if the cosmic version feels exotic. Water in a river moves not only because of the pull of gravity toward lower elevation downstream, but also because of the pressure from the water upstream pushing it along. The river flows because of a gradient, and the gradient has both a direction toward which things flow and a direction from which the pressure comes. The Milky Way is moving along a cosmological gradient with a similar structure. The attractor side provides the destination. The repeller side provides additional impetus from the rear. The repeller picture also helps resolve some of the tension in the Great Attractor story that had persisted from the earliest peculiar velocity surveys. The flow toward the Great Attractor region had always seemed somewhat larger than what the known mass concentrations in that direction could easily account for. Part of the resolution came from identifying Shapley as an additional attractor beyond the Great Attractor. Part came from better mapping the Normocluster and associated structures, and part of the remaining discrepancy was resolved by recognizing that the Milky Way was also being pushed from the other direction by the dipole repeller. The full accounting of what is moving the Milky Way through the universe at 600 kilometers per second, the number established by the cosmic microwave background asymmetry, turns out to require contributions from multiple sources: the Normocluster and the broader Great Attractor complex, the Shapley supercluster at greater distance, possibly the Vela supercluster, hidden behind the zone of avoidance, contributing an additional component whose full magnitude is still being established, and the dipole repeller pushing from the other side. No single structure owns the motion of the Milky Way. The motion is the result of a gravitational landscape that extends in all directions for hundreds of millions of light years, with mass concentrations pulling and voids pushing, the whole complex field combining into the net peculiar velocity that we measure as a 600 km per second flow relative to the cosmic microwave background. Laniakea is the basin within which all of those pulls and pushes, at least the ones on the attractor side of the watershed, combine to produce a coherent inward flow. It is the part of the gravitational landscape where the contributions add up in the same direction rather than cancelling each other out. Beyond its boundary, different attractors dominate and the flow points elsewhere. There is something clarifying about the void picture, about understanding that the shape of Laniakea is defined not just by the mass at its centre, but by the emptiness pressing in from outside. The basin is carved by both the positive and negative features of the gravitational landscape, the dense regions pulling matter inward, and the empty regions pushing it toward those dense concentrations. Structure and emptiness together produce the web. The filaments and the voids are not opposite features. They are complementary aspects of a single interconnected architecture. Laniakea has a centre, but it also has margins defined by nothing, by the absence of mass in the voids surrounding it, by the emptiness that shapes the basin as surely as the mass at its heart. The home is bounded partly by walls of matter and partly by open space. And the open space is not passive. It is part of what makes the basin a basin. Every map has an edge, not because the territory ends there, but because the survey does, because the instruments ran out of range, or the funding ran out, or the patience of the people doing the measuring reached its practical limit for that particular round of work. Every map ever made in the history of cartography is a temporary document, an honest record of knowledge as it stood at a specific moment, with the implicit understanding that the edge of the map is not a wall but a frontier. The medieval cartographers who wrote "Here be dragons" at the edges of their charts were not describing monsters. They were describing the limits of their information. The map of Laniakea has edges of exactly this kind. When Tully and his team published their 2014 paper, the cosmic flows, 2 catalogue, that formed its observational foundation covered the local universe out to a certain depth. The peculiar velocity data became sparser and less reliable beyond that depth, and the reconstructed flow field lost resolution at its outer boundaries. The watershed divide defining Laniakea was drawn within the region of reliable coverage. Beyond that boundary, the landscape continued. Other basins, other attractors, other structures of comparable or greater scale existed in the surrounding universe. Their full relationship to Laniakea, their contributions to the flows within the basin, their shapes and masses and extents, were only partially mapped. What lies beyond Laniakea is not empty space. It is a neighbourhood, a complex, structured, gravitationally active neighbourhood that has been shaping the motion of everything inside Laniakea, including the Milky Way, for billions of years. The most prominent feature of that neighbourhood, the one that had been known about the longest, and that dominated early thinking about large-scale flows in the local universe, sits roughly 650 million light-years away in the direction of the constellation Centaurus. It was identified decades before the Laniakea paper by the astronomer Harlow Shapley, who noticed in the 1930s that a region of sky in that direction contained an unusually high concentration of galaxies. Subsequent surveys confirmed and extended the observation. The concentration Shapley had noticed was real, and large, and massive. The Shapley Supercluster. Shapley is not a single cluster. It is a complex of dozens of galaxy clusters packed into a region roughly 300 million light-years across. Its most prominent members include several of the most massive galaxy clusters in the local universe, including the Abell 3558 cluster, the Abell 3528 cluster, and others that form a dense core around which less concentrated material is distributed in a broader envelope. The total mass of the Shapley supercluster is difficult to determine precisely, because the boundaries of the structure are not sharply defined, and because a significant fraction of its mass is in the form of hot intergalactic gas and dark matter rather than visible galaxies. Estimates place its total mass in the range of 10,000 to 100,000 times the mass of the Milky Way, making it one of the most massive concentrations of matter in the local universe. Shapley matters for the story of Laniakea because its gravitational influence extends far enough to affect the peculiar velocity of everything inside the Laniakea basin, including the local group. From its distance of 650 million light-years, Shapley is well beyond the boundary of Laniakea. It is in a neighbouring basin, a separate watershed with its own attractor and its own internal flow structure. But the gravitational pull of a mass concentration as large as Shapley does not stop at the Laniakea watershed boundary. Gravity has no respect for the boundaries that astronomers draw in flow field data. Shapley pulls on the Milky Way from its side of the divide, adding a component to the peculiar velocity of the local group that points in the general direction of the Centaurus constellation, roughly aligned with but distinct from the pull of the Great Attractor region within Laniakea. For many years, the Great Attractor and Shapley were considered the two dominant contributors to the observed peculiar velocity of the local group. The Great Attractor accounted for the nearby pull, associated with the Norma cluster and the broader Hydra Centaurus complex. Shapley accounted for a more distant but still significant pull in roughly the same broad direction. Together, they explain most of the 600 km per second flow that the CMB asymmetry had established. The picture felt nearly complete, close enough to move on from. Then the zone of avoidance reminded everyone that moving on was premature. In 2017, the same year the dipole repeller paper was published, Renée Kraan-Korteweg and her team at the University of Cape Town published their confirmation of the Vela supercluster. The discovery had been building for several years before the 2017 paper. A preliminary identification had appeared in earlier work using the 2-micron all-sky survey data, which hinted at a concentration of galaxies in the zone of avoidance at a distance comparable to Shapley. The 2017 study used spectroscopic redshifts from the Southern African Large Telescope and radio observations from the Meerkat Array to confirm and characterize the structure more precisely. What they found was a concentration of galaxies at roughly 800 million light-years distance, in a region almost directly behind the plane of the Milky Way, that had been invisible to every previous optical survey. The concentration was significant, not a modest overdensity easily explained away as a local fluctuation, but a genuine supercluster-scale structure comparable in estimated mass to Shapley. The team named it after the constellation in whose direction it lay, Vela. The discovery of Vela was not simply the addition of one more entry to the catalogue of known superclusters. It was a demonstration that the gravitational accounting of the local universe was still substantially incomplete. A structure comparable in mass to the Shapley supercluster had been hiding behind the galactic plane, contributing to the peculiar velocity of the local group in ways that previous models had been unable to include, because the structure had been entirely unknown. When the contribution of Vela was incorporated into the flow analysis, it improved the match between the observed CMB dipole and the sum of known gravitational influences, suggesting that Vela had been a missing term in an equation that everyone had been trying to balance for decades. The response in the astronomical community was a mixture of excitement and the particular satisfaction that comes from having a persistent residual in your data finally explained. The excitement was for the discovery itself. The satisfaction was for the reminder that the zone of avoidance was worth continuing to survey. that the effort to see through the galactic plane was not a diminishing returns exercise in filling in details, but a necessary ongoing project that continued to produce genuinely new and consequential results. Vela also raised a question about the extent to which the picture was now complete. If a Shapley scale structure had been hiding behind the galactic plane undetected until 2017, what else might be hiding there? The zone of avoidance covers roughly 20% of the entire sky. Vela was found in one portion of it. Other portions remained less thoroughly surveyed. The possibility that additional significant structures existed in the uncharted regions of the zone could not be excluded. The answer, as of the most recent surveys available, is that the zone of avoidance continues to yield results with each new generation of instrumentation, better radio arrays, more sensitive infrared cameras, and spectroscopic surveys using larger telescopes continue to push back the obscuration and reveal the galaxy population behind the galactic plane in increasing detail. The picture that emerges with each new data release is more complex than the previous one, with more structures, more detailed mass distributions, and more refined estimates of the contributions to the local peculiar velocity field. The picture is not converging toward a final, definitive answer. It is converging toward a more detailed and more accurate approximation of the truth, which is the normal situation in science and not a cause for frustration. Each improvement in the data resolves previous ambiguities while revealing new ones at finer scales. The map of the local universe beyond Laniakea is a living document, updated continuously as new surveys are completed and new analyses are published. What the current state of the surveys does tell us clearly is this: Laniakea is not the whole story of what governs the motion of the Milky Way through the universe. It is the basin we are in, the local chapter of the gravitational landscape, but the landscape extends far beyond Laniakea's boundary, with Shapley pulling from one direction, Vela contributing from behind the galactic plane, the dipole repeller pushing from the other direction, and possibly additional structures beyond those that the current surveys have not yet fully characterized. The address we are writing for ourselves in this story does not end with Laniakea. Laniakea is the layer that the cosmic flows methodology has been able to map most precisely, the level of structure at which the flow basin definition produces a clean and reproducible result. But it is embedded in a larger landscape that continues outward in every direction. And the edges of that landscape, the scale at which the local peculiar velocity field blends into the broader bulk flows of the universe, remains an active area of research and debate. Some analyses of large peculiar velocity surveys find evidence for a coherent bulk flow of the local universe on scales of 1 billion light-years or more, a motion of the entire local region that cannot be explained by any known structure within several 100 million light-years. Other analyses find no statistically significant bulk flow beyond what Shapley and the known structures can account for. The disagreement has not been resolved, and its resolution will require larger peculiar velocity catalogues with better sky coverage and more precise distance measurements than are currently available. What this means practically is that the outermost layer of our cosmic address remains, for the moment, uncertain. We know we are in Laniakea. We know Laniakea is influenced by Shapley and Vela and the dipole repeller. We know the landscape continues beyond those structures. We do not know, with the confidence that direct mapping provides, what the next layer of structure looks like or where precisely its boundaries lie. The map has edges. Beyond those edges, the territory continues, and the people making the map are following it. Let us ask the uncomfortable question directly, not the question of how large Laniakea is, or how it was discovered, or what structures lie beyond its boundary. Those questions have answers, at least approximate ones, and we have been working through them for several chapters. The uncomfortable question is the one that the discovery raises, but that most popular accounts of it prefer not to dwell on, because the answer is messier and more interesting than the clean version of the story requires. Is Laniakea real? The question sounds almost impolite after spending so much time describing the structure in detail, but it is a genuine scientific question, not a rhetorical one, and the answer reveals something important about the nature of cosmic structure, and about what it means to identify with a place at the largest scales the universe offers. Start with what we mean by real when we apply the word to structures in the universe. The question has teeth because the word does different work at different scales. The Milky Way is real in a strong sense. It is a gravitationally bound system. Its stars cannot escape it on any timescale relevant to the universe's future. They orbit the galactic center. They interact gravitationally with each other and with the dark matter halo surrounding the galaxy, and they will remain together in some recognizable form for trillions of years. If you somehow removed all external influences, froze the expansion of the universe, and isolated the Milky Way in empty space, it would continue to exist as a coherent rotating structure indefinitely. The Milky Way is real the way a solid object is real. It persists. The Virgo cluster is real in a similar sense, though at a larger scale, its member galaxies are gravitationally bound. They orbit the cluster's center of mass. They will remain together through the deep future, growing more concentrated over time as they interact and eventually merge. While the universe expands around them, the cluster is a bound object. It will persist. Laniakea is not real in this sense. The galaxies within Laniakea are not gravitationally bound to one another as a whole. The expansion of the universe, driven by dark energy, is more than strong enough to overcome the gravitational attraction between galaxies in different parts of the structure. Even though the peculiar velocities of galaxies within Laniakea currently point toward the Great Attractor region, those galaxies are not going to fall all the way in. The expansion of space will slow their infall, and eventually, for the galaxies in the outer regions of the basin, reverse it entirely. Laniakea will not collapse into a single bound object. It will, over billions of years, dissolve. The boundary of Laniakea, the watershed divide that separates it from neighboring basins, is not a permanent feature of the universe. It is a surface in the current peculiar velocity field, determined by the current distribution of matter and the current balance between gravitational attraction and cosmological expansion. As dark energy continues to work, the balance shifts. The flows weaken. The boundary shifts. The basin shrinks as its outer members lose their connection to the central attractor. What is currently a 520 million light-year basin becomes, over billions of years, a smaller and smaller remnant as the expansion carries away the galaxies that currently sit near the edges. Laniakea is temporary. It is a feature of this epoch of the universe, not a permanent fixture of cosmic geography. So is it real? The answer the science gives is not a simple yes or no, and the complexity of the answer is not a failure to resolve the question. It is the actual content of the answer. Laniakea is real as a dynamical structure. The flows that define it are physically real and observationally confirmed. The basin is a genuine feature of the gravitational potential field of the local universe. The boundary is drawn by physics rather than by human convention. The motion of the Milky Way toward the Great Attractor region, the shared trajectory of 100,000 galaxies converging toward a common center, is directly measurable and has been measured. None of this is a matter of interpretation or theoretical framework. It is observational fact. What Laniakea is not is a bound object. It is not persistent in the way a galaxy or a cluster is persistent. It is real the way a river current is real, or the way a weather system is real. These things are defined by their dynamics rather than their substance. They have measurable properties. They exert real effects on everything within and around them. They have boundaries that can be located and described, and they are temporary, lasting as long as the conditions that generate them persist, and dissolving when those conditions change. The river current is real while it flows. The weather system is real while the pressure gradient driving it exists. Laniakea is real while the gravitational landscape of the local universe has the shape it currently has. This is a different kind of reality than the reality of a rock or a star, but it is not a lesser kind of reality. It is the kind of reality that the universe assigns to its larger scale structures, the kind that requires understanding dynamics rather than just positions, the kind that rewards the patience of people who spend careers measuring galaxy motions one by one, until the pattern becomes legible. There is a deeper point here that the question of Laniakea's reality opens up, one that goes beyond the specific case of this particular supercluster, and speaks to something general about the nature of structure in the universe. Nothing in the universe is permanent in the ultimate sense. The Milky Way will exist for trillions of years, but eventually its stars will exhaust their fuel, and its stellar populations will consist mostly of white dwarfs and neutron stars and black holes, and the galaxy will be recognizable as a galaxy only in the sense that gravity still holds the remnants together in a common orbit. Galaxy clusters will persist even longer, but eventually quantum processes will erode even the remnants they contain. Black holes will eventually evaporate through Hawking radiation, over timescales so enormous that describing them requires exponents stacked on exponents. The universe assigns everything a timescale. Galaxies get billions of years. Clusters get trillions. Superclusters like Laniakea get billions. Somewhat fewer than galaxies, because the large-scale flows that define them weaken relatively quickly as dark energy accelerates the expansion. The difference between the timescales is large, but the principle is the same. Everything in the universe has a lifespan. Nothing persists indefinitely. Given that framework, calling Laniakea real on the grounds that it persists, and calling it not real on the grounds that it is temporary, are both doing something slightly dishonest. The question is not whether it is permanent, because nothing is. The question is whether it is a genuine feature of the universe right now, in this epoch, with these physical conditions. And the answer to that question is clearly yes. The flows are real now. The basin is real now. The boundary is real now. The Milky Way is inside it now. These facts are as well established as any observational result in modern cosmology. What Laniakea teaches us, if we are willing to accept the lesson it offers, is that home does not require permanence. The largest home we can currently identify for ourselves in the cosmos is defined by motion rather than walls, real by virtue of its dynamics rather than its substance, and temporary in the way that all things are temporary when measured against the full lifespan of the universe. That is not a diminishment. A home defined by shared motion and common trajectory, by the gravitational landscape that places you within a particular basin and points your galaxy toward a common center with 100,000 others, is still a home. The flows are real. The belonging is real. The fact that the flows will weaken over billions of years does not make the belonging false. It makes it specific to a time, which is the condition of every meaningful thing in the universe. You live inside a basin defined by how things move. The basin has a name. The name means immeasurable heaven, and it is real in every sense that matters for the moment you are in, which is the only moment you have ever been in or will ever be in. That is enough. There is a kind of beauty that only becomes visible when you understand that something is temporary. A cherry blossom in full bloom is not more beautiful because it lasts. It is more beautiful because it does not. The brevity is not incidental to the beauty. It is constitutive of it. The Japanese have a word for this. Mono no aware. The bittersweet awareness of impermanence. The particular emotional quality that attaches to things precisely because they will not last. It is one of the most nuanced emotional concepts in any human language, and it describes something that the science of Laniakea makes available as a felt experience. If you are willing to sit with the full picture of what Laniakea actually is, Laniakea is beautiful, and Laniakea will not last. We have already established this in the context of asking whether Laniakea is real. We said that it is real as a dynamical structure, real as a basin in the gravitational landscape of the current universe, real in the way that a river current is real or a weather system is real. And we said that this kind of reality comes with a time scale, that the flows defining the basin will weaken as dark energy continues its work, and that the structure will dissolve over billions of years as the expansion carries away the galaxies that currently sit near its edges. But saying it in passing and sitting with it fully are different things. What it means for the home to be dissolving, what it means for the largest address we can currently write for ourselves to be temporary in a way that is not just abstractly true but physically inevitable, deserves its own space, its own careful attention, its own chapter. The force responsible is dark energy. Dark energy is the name we give to the component of the universe responsible for the accelerating expansion that two independent teams of astronomers discovered in 1998. While studying distant Type Ia supernovae, both teams had set out to measure the deceleration of the cosmic expansion, the rate at which gravity was slowing down the outward motion that the Big Bang had imparted. What they found instead was that the expansion was not decelerating. It was accelerating. The universe was not just expanding. It was expanding faster and faster as time went on. This was not expected. The discovery earned its principal investigators, Saul Perlmutter, Brian Schmidt, and Adam Rees, the Nobel Prize in Physics in 2011. It was, by most accounts, the most surprising cosmological discovery since Hubble's identification of the expansion itself, and it implied something deeply counterintuitive about the composition of the universe. Something was counteracting gravity on the largest scales. Something was pushing the expansion faster rather than letting gravity slow it down. That something was dark energy. The leading theoretical candidate for dark energy is the cosmological constant, a term that Einstein introduced into his field equations in 1917. When he was trying to construct a static universe, Einstein added the constant as a kind of universal repulsion, a property of empty space itself that would balance the gravitational attraction of matter and keep the universe from collapsing. When Hubble's observations revealed that the universe was expanding rather than static, Einstein reportedly called the cosmological constant his greatest blunder and abandoned it. The irony is that the constant may have been right all along, just for the wrong reason. The universe is not static, but empty space does appear to have an energy density that drives the expansion, and the cosmological constant is the simplest mathematical description of that energy density. Whether the cosmological constant is the correct description of dark energy, or whether dark energy has some more complex character that will reveal itself in future observations, is still unknown. What is not unknown is its effect. Dark energy causes the expansion of the universe to accelerate, and the acceleration changes the long-term fate of every structure in the cosmos that is not gravitationally bound tightly enough to resist it. At small scales, gravity wins easily. The Milky Way is not going to be torn apart by dark energy. The gravitational binding energy of the Milky Way is far larger than the dark energy density within its volume. The local group is similarly safe. The mutual gravitational attraction between the Milky Way and Andromeda, and between all the smaller galaxies of the local group, is more than sufficient to keep the group together indefinitely, even as dark energy accelerates the expansion of the space around it. When Andromeda and the Milky Way eventually merge into Milkdromeda, the resulting galaxy will remain bound, its stars held together by gravity that dark energy cannot overcome at those scales. The Virgo cluster will hold together. The Norma cluster at the heart of the Great Attractor region will hold together. Individual galaxy clusters throughout Laniakea will hold together. Their gravitational binding energies are large enough that dark energy, operating at the energy densities it currently has, cannot unbind them. But Laniakea as a whole is a different situation entirely. Laniakea is defined by flows, not by binding. The galaxies in its outer regions are not tightly bound to the central attractor. They are participating in a flow that currently points inward. But the net gravitational pull drawing them toward the center is not large compared to the dark energy density operating across the vast spaces separating them from the Norma cluster region. As dark energy continues to drive the expansion faster and faster, it will increasingly counteract the inward, peculiar velocities of those outer galaxies. The galaxies will slow their approach, stop, and then, over billions of years, begin to move outward instead, carried away by the expansion of space. The process will not be sudden. There is no specific moment when Laniakea ends. The boundary does not snap. The flows do not stop all at once. What happens is a gradual weakening, a slow erosion of the coherence that defines the basin. The outermost galaxies, the ones currently closest to the Watershed divide, are the first to lose their connection to the basin. Then the next layer, then the next, over billions of years. The effective boundary of the coherent inward flow contracts. As dark energy peels away the outer layers of the structure and carries them into a future where the expansion dominates over any local gravitational pull they might have felt. What will be left, after enough time has passed, is not Laniakea. It will be the individual gravitationally bound clusters and groups within the basin, each one still internally coherent but no longer connected to each other by a common flow. The Norma cluster region will still exist. The Virgo cluster will still exist. The local group, already having merged into Milky Way by that point, will still exist, but they will be islands, separate, disconnected, drifting apart in an expanding universe, with no common flow to bind them into a coherent structure. Laniakea will have become its remnants. The timescale for this dissolution is difficult to state precisely, because it depends on assumptions about the future behavior of dark energy that are not fully constrained by current observations. If the cosmological constant description is correct and dark energy maintains a constant energy density as the universe expands, the dissolution of Laniakea's coherent flow structure will proceed over tens of billions of years. If dark energy has a different character, if its energy density changes with time in ways that current observations cannot rule out, the timescale could be longer or shorter. What is not uncertain is the direction of the process. The flows will weaken, the basin will contract, the outer members will be carried away. The structure that Tully and his team mapped in 2014 will not be mappable in the same way 10 billion years from now. Not because the data will be insufficient, though it will, but because the structure itself will have changed into something that the watershed definition no longer recognizes as a coherent basin. The local group will hold. Milky Way will hold. The individual clusters will hold. But the 100,000 galaxies that currently share the Laniakea basin will not all remain reachable. The more distant ones are, in a sense, already on a countdown. The expansion is already working on them, already opposing their inward drift, already shortening the window during which the flow that connects them to the basin will remain strong enough to define them as members of it. There is a particular sadness available in this information that does not require any exaggeration to feel. The largest home we can name for ourselves is already coming apart. Not quickly, not dramatically, not in any way that matters on human timescales or even on the timescale of life on Earth. But cosmically, the dissolution is already in progress. Dark energy does not wait for convenient moments. It works continuously, at every point in space, with a patience that makes the patience of geological processes seem hasty. And yet, the dissolution of Laniakea does not mean that the universe is becoming worse. It means that the universe is evolving. The cosmic web of today, with its rich structure of filaments and clusters and supercluster basins, represents a particular phase in the history of the cosmos, a phase when gravity and dark energy are in a kind of ongoing contest, and when gravity is winning at small enough scales to produce the rich architecture we observe. In the future, dark energy will gradually win at larger and larger scales, dismantling the large-scale structure while leaving the small-scale structure of galaxies and clusters intact. The universe is not ending, it is changing, moving from a phase of complex large-scale structure to a phase of simpler large-scale structure, with complexity preserved at smaller scales. The rivers of the cosmic web will fade while the islands they connected remain. This is, if you hold it without flinching, a kind of loss. The addresses will get shorter. The maps will get simpler. The Milky Way of the far future will still be there, still gravitationally bound, still internally complex, still perhaps harbouring some form of intelligence on some surviving planet, orbiting some surviving star. But that future civilization, looking outward from their island galaxy, will see a universe that has forgotten its own large-scale structure, a universe that no longer has visible evidence of the cosmic web that once organized it, a universe that looks simpler than it was, because the simplifying has been underway for long enough to reach completion. They will not have Laniakea. The flows will have stopped. The basin will have dissolved. The watershed will have faded into the smooth, featureless expansion of space between isolated island galaxies. We have it now. Right now. In this epoch. The flows are running. The basin exists. The boundary can be drawn. The address can be written. The name Laniakea refers to a real, coherent, physically meaningful structure in the universe that the Milky Way currently inhabits. And that fact, the fact that we exist at a time when this structure is present and mappable and nameable, is not something to set aside as a mere coincidence of timing. It is the condition of everything meaningful we have ever known or done or been. It is the condition of being here, in this universe, at this moment, inside the immeasurable heaven that will not hold forever, but is holding now. Step outside on the right night, somewhere far from city lights, and the sky is extraordinary. The Milky Way runs overhead in a broad, uneven river of light, brighter in the direction of the galactic centre, dimmer toward the outer arms, crossed by dark lanes of dust that cut through the luminosity like shadows in the fabric of the galaxy. Individual stars are so numerous that the familiar constellations dissolve if you look too carefully, swallowed by the background density of fainter stars that the dark-adapted eye can just resolve. If you know where to look, Andromeda is there, a faint smear above the horizon in the autumn sky. Its light 2.5 million years old by the time it reaches you. With a telescope of even modest aperture, you can see galaxies in the Virgo cluster, 65 million light-years away. With patience and good conditions, you can trace the faint extension of the Virgo concentration across a wide swath of sky. Dozens of galaxies visible in a single field of view, the nearest major node of Laniakea spread out before you in the eyepiece. The sky you can see tonight is rich with information. It contains light from the local universe going back hundreds of millions of years. It contains the signatures of the large-scale structure, the overdensities and underdensities that trace the cosmic web, the nearby galaxies and clusters that define the neighborhood Laniakea occupies in the cosmos. It contains, for those with the instruments and methods to read it, a record of the flows and basins and watershed divides that make up the gravitational landscape of the local universe. It will not always look this way. The sky of the far future will be different in ways that go beyond the gradual proper motion of nearby stars changing the shapes of constellations, or the merger of Andromeda with the Milky Way, transforming the night sky of any surviving planet over millions of years. Those changes are significant, and they will make the sky unrecognizable to anyone familiar only with today's night sky. But there is a deeper change coming, one driven not by the motions of nearby objects, but by the relentless acceleration of the cosmic expansion. The galaxies of the local universe are moving away from us. Most of them. The ones outside the local group, outside the small gravitationally bound cluster of galaxies that will remain coherent even as dark energy does its work, are all receding, and as dark energy accelerates the expansion, they are receding faster and faster, not because they are moving through space at increasing velocity, but because the space between us and them is expanding at an accelerating rate, stretching the distance even as the galaxies themselves move through space in complex ways. There is a consequence of accelerating expansion that has no analogue in ordinary human experience. At sufficiently large distances, the recession velocity, the rate at which the space between us and a distant galaxy is increasing, exceeds the speed of light. This does not violate relativity, because nothing is moving through space faster than light. It is the space itself that is expanding, and there is no limit in general relativity on how fast space can expand. But the practical consequence is that light emitted by a galaxy beyond a certain distance, the cosmological event horizon, will never reach us. The galaxy exists. The light is travelling toward us, but the space between us and the light is expanding faster than the light can cross it, and the photons will never arrive. The cosmological event horizon is not fixed. It depends on the rate of expansion, which is changing as dark energy drives the acceleration. In the current epoch, the event horizon lies at roughly 16 billion light-years. Galaxies beyond that distance are currently inaccessible to any future signal we might send or receive. As the expansion accelerates, the event horizon shrinks, not in absolute terms, but in the sense that the number of galaxies within our reachable universe decreases over time. Galaxies that are currently within the event horizon will eventually be pushed beyond it as the expansion carries them away. The Virgo cluster, 65 million light-years away, is well within the event horizon and will remain reachable for an extraordinarily long time. The Shapley supercluster, 650 million light-years away, is also within the current event horizon, though it is far enough that the long-term situation is less certain, depending on the future behavior of dark energy. Galaxies at the distances of the most remote structures currently observable, billions of light-years away, are in various stages of recession toward and eventually beyond the horizon. On a timescale of 100 billion years or so, something will have happened to the night sky that represents one of the most profound changes in the observable universe since the formation of the first galaxies. The galaxies outside the local group will be gone, not destroyed, not consumed, just receded. The light they are currently emitting will still be traveling through the universe, but it will be so extremely redshifted by the time it reaches the position the local group occupies that no instrument imaginable could detect it. The galaxies will have crossed beyond the cosmological event horizon, becoming causally disconnected from our region of the universe. They will still exist, but they will be, for all observational purposes, absent. The night sky viewed from the future Milky galaxy will be nearly empty of external galaxies. Nearly. Not completely. The very closest members of the original local group, already merged or closely bound to Milky, will still be visible. The remnants of the Magellanic Clouds, long since absorbed. Perhaps a few surviving dwarf galaxies that were tightly enough bound to the local group to remain within its gravitational reach. But the broader universe, the Virgo cluster, the Great Attractor region, the Shapley supercluster, the cosmic web itself, all of it will be gone from view. The inhabitants of Milky, if any exist, will look out at a universe that appears to consist of a single galaxy surrounded by darkness, not because the universe is empty, but because the universe has expanded beyond the range of observation. They will have no evidence from direct observation that any other galaxies exist. If they conduct surveys of their night sky expecting to find the cosmic web of filaments and voids that modern astronomy has mapped, they will find nothing. The sky will appear isotropic and empty beyond their own galaxy. If those future inhabitants are scientists, they will face a cosmological puzzle that we, living in the current epoch, are fortunately positioned to recognize, but that they would have no way to independently solve. Why is the cosmic microwave background, if they can still detect it, so uniform and isotropic? What produced the heavy elements in their stars, given that no large-scale structure is visible to explain the distribution of matter? Why does their galaxy have the chemical composition it does? The answers to those questions are written in the large-scale structure of the universe, in the distribution of galaxies and clusters and voids that traces the history of structure formation from the early universe to the present. But by the time 100 billion years have passed, that record will be largely inaccessible. The light from the early universe, the cosmic microwave background, will have been redshifted to wavelengths so long that detecting it would require instruments of an implausibly enormous scale. The nearby galaxies whose properties encode the history of nucleosynthesis and chemical evolution will have receded beyond observation. The universe will have hidden its own history. This is not a conjecture or an extrapolation beyond what the science supports. It follows directly from the established properties of dark energy and the accelerating expansion. The cosmological event horizon is a real feature of the universe, and the recession of galaxies beyond it is a real and ongoing process. The only reason we can observe the vast wealth of structure that modern astronomy has mapped is that we happen to live in an epoch when the expansion has not yet carried most of it beyond reach. Astronomers sometimes describe this as the fortunate epoch of observation. The universe is rich enough in visible structure right now to tell its own story completely. The cosmic microwave background is detectable and carries information about the earliest phases of cosmic history. Distant galaxies are visible and their redshifts encode the history of the expansion. The large-scale structure of the cosmic web is mappable with current technology. All the evidence needed to reconstruct the history of the universe, from its beginning to the present day, is available in the sky tonight. In the far future, almost none of it will be. The future sky will be dark and simple, where the present sky is rich and complex. The present sky contains Laniakea, at least in principle, accessible to instruments sensitive enough to measure the peculiar velocities of its member galaxies. The future sky will contain only the island of Milkdromeda and a handful of gravitational satellites, surrounded by an expanding darkness that gives no hint of what it once contained. We are here now. The sky is full. The flows are running. The basin exists and has a name. That is not nothing. In the full sweep of cosmic time, it is a great deal. It is everything that makes the current epoch of the universe the extraordinary moment in cosmic history that it is. The moment when a conscious species, living on a small planet in the outer arm of a spiral galaxy in the outer reaches of a supercluster basin, developed the instruments and the methods and the patience to read the motion of the universe and find their address in it. The window is open. It will not always be. And tonight, it is still letting in light from the full depth of the cosmos, from galaxies that are already receding but have not yet gone, from the large-scale structure of a universe still young enough to show its own history in the sky. Come back to where we started, not to the beginning of the universe or the formation of the first galaxies, just to the beginning of this particular story, to the image we opened with, the one that has been quietly present in the background through every chapter since. You, lying in the dark, not standing still. That image was not chosen as a poetic device. It was chosen because it is true at every scale simultaneously, and because the experience of lying still while being in motion at every scale of your address is, when you hold it fully, one of the more remarkable conditions any creature in the history of this planet has ever occupied. You feel the stillness. The room is quiet. The weight of the day has lifted. Nothing about the sensory experience of that moment communicates the 600 kilometers per second of peculiar velocity carrying the Milky Way toward the Great Attractor region, or the 230 million year galactic orbit of the Sun, or the 67,000 miles per hour that Earth adds as it rounds its annual corner around our star. The stillness is not an illusion exactly. It is a scale-dependent truth. At human scales, in human time, you are still, at cosmic scales, across cosmic time, you have never been still for a single moment since before the Earth existed. What changed over the course of this story is not the motion. The motion was always there. What changed is the framework for understanding it. When Hubble measured the distance to Andromeda in 1923 and found that the universe was larger than anyone had imagined, the framework changed. When the CMB asymmetry established that the Milky Way had a 600 km per second peculiar velocity relative to the early universe, the framework changed. When the Seven Samurai spent years measuring peculiar velocities across the sky and concluded that something they called the Great Attractor was responsible for coordinating the flows of the local universe, the framework changed. When Tully and his collaborators spent decades building the cosmic flows catalogues, developing the Watershed methodology, and published their 2014 paper naming the basin the Milky Way was part of, the framework changed one more time. Each change made the address longer. Each change revealed that the layer we thought was the outermost layer had another layer behind it. And each change required not just new instruments, but new ways of asking the question. Not just what is out there, but what are the things out there doing? The deepest conceptual shift in this entire story is the one from mapping positions to mapping motions. It seems technical when stated as a methodological point, but its implications run further than methodology. Mapping positions assumes that the universe can be captured in a snapshot, that if you could freeze everything in place and measure where it all was, you would understand the structure. Mapping motions assumes instead that the universe is fundamentally dynamic, that what things are is inseparable from what they are doing, that structure cannot be separated from dynamics, that you cannot understand what a galaxy belongs to without knowing where it is going. This is not just a practical observation about how to do better cosmology. It is a claim about the nature of cosmic structure. The structures that exist at the largest scales in the universe, the superclusters and their basins, are not objects in the ordinary sense. They are patterns in a flow. They are the cosmic equivalent of eddies in a river or cells in a convecting fluid, coherent and organized and real, but defined by their dynamics rather than their substance. They exist because the universe is in motion, and they would not exist if the universe were not in motion. Laniakea is not a container that the Milky Way happens to be inside. It is a current that the Milky Way is part of. The difference between those two descriptions might seem subtle, but it changes everything about what it means to belong to the structure. If Laniakea were a container, membership would mean enclosure. Being inside it would mean being bounded by it, limited to it, unable to leave it. And the news that the container was dissolving over billions of years would be a kind of existential threat to that membership. If the walls are coming down, we are losing our home. But Laniakea is a current, and membership in a current means participation in a flow. Being inside it means moving with it, sharing its trajectory, being part of the same organized motion as 100,000 other galaxies. And the news that the current will weaken over billions of years is not a threat to the membership. It is simply information about the timescale of the flow, about how long the pattern will remain coherent before the conditions that generate it change. The current is real now. The participation is real now. And participation in something real, even something temporary, is a different kind of belonging than enclosure in something permanent. The Polynesian navigators who gave their language to Laniakea understood this distinction in a way that their tradition encoded directly into its practice. A Polynesian navigator did not belong to the ocean by being contained in it. No canoe contains an ocean. The ocean is the medium the navigator moves through, the dynamic system that the navigator reads and responds to, and works with rather than against. Belonging, in that tradition, meant being skilled enough at reading the flows to move confidently within them, knowing where the currents were and how they were running, being oriented rather than lost. The method that found Laniakea is the same method in a different medium. The Cosmic Flow surveys did not find Laniakea by drawing a circle around a dense region of the galaxy catalogue. They found it by reading the flows, by measuring the peculiar velocities of thousands of galaxies spread across the local universe, and reconstructing the gravitational landscape that the velocities implied, by finding the basin, the region of convergent flow, and drawing its boundary at the Watershed divide where the flows change direction. The method said, we are in a current. The current has a shape. The shape has a name. Now, here is what the current tells us about where we are, stated as simply as possible. We are in the outer reaches of a gravitational basin 520 million light-years across. The basin is called Laniakea. Its central concentration is the Great Attractor region, associated with the Norma cluster and the broader Hydra-Centaurus complex, roughly 250 million light-years from the Milky Way in the direction of the constellation Centaurus. The Milky Way is moving toward that region at a component of its total peculiar velocity that reflects Laniakea's contribution. It is also being pulled by Shapley from beyond the basin's edge, and pushed by the dipole repeller from the other direction, and influenced by the distributed mass of everything in the cosmic web that exerts a gravitational pull across hundreds of millions of light-years. The motion is complex, the address is long, and both the motion and the address are still being worked out. With each new generation of peculiar velocity surveys, adding data points, refining the flow field reconstruction, extending the coverage, and revealing new structures in the regions that previous surveys could not reach. The address does not end with Laniakea. Laniakea is the layer that the current methodology can define most precisely. The level of structure at which the watershed concept produces a clean and physically motivated result. But the landscape beyond Laniakea continues, with Shapley and Vela and the dipole repeller contributing to flows that extend across scales larger than the basin itself, and with the possibility of additional structures beyond those that the current surveys have not yet characterized. The address is incomplete. The map has edges. The territory continues beyond those edges in directions that have not yet been fully surveyed. That is the normal condition of knowledge in a universe that does not sit still while you measure it. It is not a failure. It is an invitation. Every generation of astronomers has stood at the edge of the map, looking outward at territory that their instruments could not quite reach, and built better instruments to extend the reach. Hubble stood at that edge in 1923, when he measured the distance to Andromeda with Cepheid variables on a California mountaintop. The Seven Samurai stood at that edge in the 1980s, when they compiled their peculiar velocity catalogue and pointed toward a mass concentration that nothing in the existing maps could explain. Tully and his collaborators stood at that edge for decades. As the Cosmic Flows project grew from a few thousand galaxies to tens of thousands, each iteration revealing more of the flow field than the previous one. The people now extending that work, building larger radio arrays, improving distance measurement techniques, extending redshift surveys into previously unmapped regions of the sky, including the zone of avoidance, stand at the same edge. They are adding lines to the address. They are filling in the map. They are reading the flows and finding what the flows are telling them about the structure we are part of, and the structures beyond that. You are here, in a basin with a name, part of a current that has been running for billions of years and will continue running for billions more, weakening slowly as dark energy does its long, patient work, but running clearly enough right now that its shape can be mapped, and its boundary can be drawn, and its name can be spoken. The name means immeasurable heaven. It was chosen by people who crossed an immeasurable ocean by reading how it moved. The parallel is not accidental. It is the point. We found our place in the cosmos the same way their ancestors found their place in the Pacific, by watching how things moved around us, by following the flows to their source, by reading the current until the current told us where we were. And now we know. Not completely, not finally, but enough to say we are here. In this basin, part of this flow, moving with 100,000 other galaxies toward a center that the gravitational landscape of the local universe has been pointing us toward, for longer than the Earth has existed. That is the address. That is the story of how we found it. And the story is not finished, because the map is not finished. And the map is not finished because the universe is not finished. And the universe is not finished because the universe has never been standing still. You are not standing still. We said that at the beginning. We say it again now. And the words carry more weight than they did the first time you heard them. Not because the motion is different. The motion is exactly what it was before you heard any of this. The Earth is still spinning at the same rate. The Sun is still moving through the Milky Way at the same speed. The Milky Way is still flowing toward the Great Attractor at the same velocity. None of that changed while we were talking. What changed is what you know about it. The address you had before this story was Earth, in the solar system, in the Milky Way, familiar layers, well established. The kind of address that gets printed in textbooks and recited in science classrooms, and that most people carry through their lives without feeling the need to go further. A good address. True as far as it goes. The address you have now goes further. Earth. Third planet from a medium-sized star. In the outer arm of a barred spiral galaxy containing between 200 billion and 400 billion stars. That galaxy, the Milky Way, is one of roughly 80 members of a gravitationally bound family called the Local Group, dominated by two spirals, the Milky Way and Andromeda, falling toward each other at roughly 70 miles per second and destined to merge in about 4.5 billion years. The Local Group sits near the edge of a much larger structure, the Virgo Supercluster complex, itself part of a flow basin 520 million light-years across that was mapped for the first time in the year 2014 and given the name Laniakea, immeasurable heaven, in the Hawaiian language. That basin, Laniakea, is defined not by walls but by motion. Its boundary is a watershed divide in the gravitational landscape of the local universe. The surface where peculiar velocity flows that converge toward the Great Attractor region give way to flows pointing toward other basins. The Milky Way is inside that boundary, part of the inward flow, moving with 100,000 other galaxies toward a center it will never actually reach, because dark energy will continue to work on the outer layers of the structure long before the infall could complete. The address is temporary at its outermost layer. Laniakea will dissolve over billions of years as dark energy weakens the flows that define it. The local group will survive the dissolution, held together by gravity strong enough to resist the expansion indefinitely, but the 100,000 galaxies that currently share the basin will drift apart, and the structure we call Laniakea will become a memory encoded in the peculiar velocities of isolated clusters and groups that were once part of a common flow. Future inhabitants of Milkdromeda, the galaxy that will form when the Milky Way and Andromeda complete their merger. I will look out at a night sky nearly empty of external galaxies. The cosmic expansion will have carried everything outside the local group beyond the cosmological event horizon. They will have no way of knowing that their galaxy was once part of a 520 million light-year basin called Laniakea. The evidence will be gone. The flows will have stopped. The address will have become unwritable. We can write it now. That fact, the fact that we exist in the window of cosmic time when the evidence is still present, and the instruments are sensitive enough to read it, and the methods have been developed to interpret what the instruments find, is worth holding clearly, not as a reason for self-congratulation, not as evidence that the universe arranged itself for our benefit, as a simple statement about where we are in the history of a cosmos that is always changing, and that happens right now, to be in a phase when its large-scale structure is both present and legible. The window opened when the first peculiar velocity surveys were completed in the 1970s and 80s. It will close, slowly, as dark energy continues to work, and as the structures that the surveys mapped dissolve and recede beyond observation. In between, there is a period when a species on a small planet in the outer arm of a spiral galaxy can build instruments sensitive enough to measure the motions of thousands of galaxies across hundreds of millions of light-years, and reconstruct from those motions the shape of the gravitational basin they are part of. We are in that period. Right now. Tonight. The Cosmic Flows project is still running. New data is being collected. Each new iteration of the catalogue extends the reach, improves the resolution, fills in the blanks that previous surveys left. The zone of avoidance is still being mapped, still yielding surprises, still containing structures that had been invisible until instruments sensitive enough to penetrate the galactic plane were pointed in the right direction. The outer edges of the Laniakea map are still being refined, as improved data resolves ambiguities in the flow field reconstruction that the original 2014 paper could not fully address. The address is being extended, one measurement at a time, one galaxy at a time, one careful question at a time, and somewhere in that ongoing work, in the patient accumulation of redshifts and distance measurements and peculiar velocity calculations that constitutes the daily practice of large-scale structure astronomy, there may be discoveries waiting that will add new layers to the address, new structures beyond Laniakea that the current surveys have not yet resolved, new features of the gravitational landscape that will require revisions to the boundary of the basin or the flow field within it, new surprises from the zone of avoidance that will change the accounting of what is pulling the Milky Way through the universe. The map will not be finished in our lifetimes. It may not be finished for generations. The universe does not cooperate with deadlines. But right now, tonight, the map exists out to the boundary of Laniakea. The address can be read out to that layer. And the address, read in full, places you somewhere specific in the largest structure humanity has ever been able to name as its own. You are in the outer reaches of a gravitational basin 520 million light-years across. You are part of a flow that has been running since long before the Earth existed. You are moving with 100,000 galaxies toward a center defined by the gravitational landscape of the local universe. Under a sky still rich with the light of a cosmos that has not yet hidden its own history from the people living inside it, you are not standing still. You never were. And now, for the first time in the history of your species, you know something about the direction of the current you are in, the shape of the basin you are part of, and the name that immeasurable heaven was given on the day that a group of careful, patient people finished reading the motion of the universe well enough to say, "This is where you are." Laniakea. Immeasurable heaven. Yours. For now. And for as long as the window stays open,